So it's 2 o'clock. I think time to start again. I think most of you are back. So you found the way to this room. Also on the live stream, we still have some participants. We didn't lose all of them, so that's good. Welcome again to this afternoon session, which will be all about modeling. So we will talk about modeling of fracture, transport, durability, and self-healing. And I will not do that all by myself this afternoon, but Branko, Šavija, and Claudia, Romero, Rodriguez will join. I will do the first hour talking about fracture, and then those two will talk about the other aspects, transport, durability, and how you can apply it for self-healing. On screen. So if you are going to do modeling, then the goal, the aim of modeling should actually be to design safe, reliable, and optimal structures. Or maybe to design better, fit for purpose, stronger and reliable materials. So that's what we want to do. That's why we want to apply modeling to achieve that. And of course, you can also use it to design your experiments, that you want to do for your project to study self-healing mechanisms. So for that, modeling is also a great tool to use that. So you can model concrete as a homogeneous material, and of course, especially you do that if you simulate large structures. Then you are not going to model it all at the material level, but you can also decide to really model it on the level of the components of the material. Then you really zoom in, and especially if you want to develop materials, if you want to study things that happen in the material, the microstructure is important, then you should study it as a heterogeneous material and also apply it like that in your model. So if you model it as a homogeneous material and you want to simulate fracture, so what we discussed yesterday morning, so when I explained about all the fracture mechanisms, then I also showed this model, the fictitious crack model of Hilleborg, and that's what often is applied when you study concrete as a homogeneous material and you do simulations. So then you have this softening curve, and you model it as 2 parts. One part is where this elastic up to a certain strength, and then if at some point you exceed the strength, then it goes into this softening regime, where it follows this curve, and we take all these aspects, so the stiffness of the material, the strength, and this GF, the area under the curve, take that into account in the numerical model. So then there are basically 2 ways to implement such a behavior into a finite element tool, finite element model. One is a discrete, and one is a smear crack approach. And in a discrete crack approach, you actually work with the crack opening of the material. So you simply say that if the stress here at the bottom exceeds the tensile strength, then what you do is you split the nodes in 2, and the behavior between those nodes that follows this softening regime, and that's how then the crack can propagate through your material. You can also use a smear crack approach, so then you actually use the strain of the material. So here at the top you use the crack opening. At the bottom you use the strain of the material, and the strain you smear out over an element or over several elements. So that is your crack bandwidth actually that you use to implement in the model, and in that way you simulate fracture. Then these elements, they follow also this softening curve that we saw in the previous graph. this was the softening curve. It's better to use my mouse to my pen to draw. So this is basically the two approaches. There are some differences, different approaches also available, but this are the basics, so a smear and a discrete crack approach. And then if you model materials, if you model fracture, on this large scale, you can model concrete elements, part of a structure, you can model a whole building, or you can model a complete bridge, as you see here, using these finite element tools and simulate fracture at certain locations in these models. You can also use finite element tools to simulate on the heterogeneous level, to really zoom into the material. But there's also another approach to simulate fracture on these levels. So that's what we often use in Delft. It's a discrete crack approach, because we think it's much more easier and straightforward to simulate fracture in a material with these kind of models. Especially if you have multiple cracking in the material, then this discrete crack approach seems to be giving better results, and it's also easier to implement. And we like easy models, because if it becomes too complicated, then we don't understand it anymore. So that's why we use these discrete models. So the general procedure is that you make a network, as you see here, a network of elements you see here, which can be 2D or 3D, and all these elements, they can transfer forces. For civil engineers, that should be easy, because it are normal forces, shear forces and bending moments. So they are just beams in 2D, and in 3D they also can transfer torsional forces. And each of these elements is linear elastic, is brittle. At least that's the principle. So they follow a certain stress strain curve, linear elastic. If they reach the strength, then we say this element will fail, and we just take it out of the network. So then you have a network where this element maybe fails. That has the highest stress of all of them. Well, the highest stress compared to its own strength, because they don't have to have all the same strength in the material. But yeah, these elements break first, you take it out and you do a new analysis. Again, apply the same load, and then the next element, maybe this one will fail. And then this one will fail for the next simulation. And in that way, you propagate the crack to the system. So in these two examples that you see here, this dog bone, which is loaded vertically, the white elements are the elements that crack, and then it breaks, and it, well, you get a very large displacement, as you see here. But that's how the crack propagates to the material. Also this one, this prism with two notches, you stretch it, and of course the elements at the notch will start to break first, and that's how you propagate the crack to the system. And in the simulations, you say you load this network with a force or a displacement, and it's just a linear elastic analysis. So just linear elastic, you solve all the forces in the network, you take out one element, and you do again a linear elastic analysis. So it's a sequential linear elastic analysis. So you always find a solution, and it's quite fast. Even for large networks, you can propagate a crack within minutes, hours, or days, depending on your computer that you have and how big you make your system. I already said that the strength of all the elements doesn't have to be the same. So especially if you want to simulate the microstructure, so if you want to simulate the heterogeneous material, you have to implement some kind of disorder or microstructure. So you can do that by just do a random variation of the properties, but you can also generate a grain structure, like you see here in 2D. You have circles, and then you give different properties to the elements, which are in the cement matrix here, which are inside an aggregate or at the interface in between them. So you give 3 different types of strength and stiffness, and you do then the simulation. You can also make this. So this is a regular structure with regular triangles, but you can also use random triangles like you see here. That already gives you some heterogeneity to the material. You can also go to real images of material, like you see here. This is a microscopy image from a cement paste or a mortar, actually. So these are aggregates, and you have cement matrix in between, and also porosity here. So this is the real image. You use some image processing that you come up with a 3-phase material, and then you again put the network with all these small beams on top of it and give different properties to the different regions, and then you do a simulation. And of course you can do this in 2D, but you can do the same in 3D, but then you need of course a 3D image, which you can get from a CT scan, for instance. We did in the past a lot of fracture analysis, so uniaxial tension. We did 4-point shear, here tensile splitting or compression. So you can model nicely crack propagation in these materials. We also applied it to different mechanisms, like this is frost sol scaling, where we had water inside the porosity. So here you have the pores, and inside the pores you have water that freezes, becomes ice, and is going to expand and creates then cracks in your system, like you see here, which looks similar to the one that we observe experimentally. So you can simulate these real mechanisms. And in this case, we don't have an external load, but it's an internal load. So the elements inside the pore, which were water, they freeze and they expand. So you can also have an internal loading in the material. We did frost sol scaling analysis. Let's see, this should work. So you see frost sol scaling, like was presented by Valenza and Shearer already some years ago, where they said, well, the scaling of concrete at the surface is because you have a layer of water on top that you see here, the black region, that this is water, and this water will freeze, it will become hard, it will shrink due to the temperature decrease, but it also this mortar, this concrete will shrink, and they have a difference in expansion coefficient. So that means that at some point the ice will crack, and the ice cracks, and then the crack will propagate into the concrete and takes out a chunk of material, and that was how they explained frost sol scaling. So that we also did with the model, and it came nicely out without changing any properties. It just came out by itself. And you can do self-healing, then you just do it back and then it's healed again. So that's also nice with the model. So you see you can fracture it and you heal it again. Well, of course, we want to apply this also on multiple scales. So we want to do multiple scale modeling because all the mechanisms in concrete happen at different scales. So fracture happens at different scales, but also hydration, moisture flow, temperature, diffusion, expansion of rebars. So all these aspects we want to simulate with this type of modeling. And then you have to go from one scale to the other. So I will show that now how we do that for fracture, but you can do the same for moisture and for other transport mechanisms, like Branko and Claudia will explain later on. So multi-scale modeling, you can go from cement paste to mortar to concrete. So Ziwei Chen did his thesis about that, so that you first simulate something on the cement paste level that you include into a mortar level, or first a paste level where you include some sand particles. You simulate it there, and that goes into the real concrete element, which has aggregates and matrix around it. And those aggregates can of course be non-spherical, but can have any shape that you want. And the shape in this case we got by putting aggregate particles also in the CT scanner, and then we have the shape of the particles, which we then can include in the model. So what we do then is we transfer the properties we get from the cement base scale to the mortar scale, and then we transfer that to the concrete scale. That's the way we do multi-scale modeling. But you still also need properties. So if you do modeling on all these scales, you also have to measure your properties on each scale, and you have to do validation. So how to get the local properties? So then we also have to do small scale testing. So we do small scale testing like a tensile test with a very small tensile testing machine, or a bending of a small prism that you see here, 3-point bending. We do CT scans to get images of the material that we can implement in our model, so that we know the microstructure that we can use in the model. And we also saw yesterday that we used nano indentation to get locally properties of the constituents in our model, so of the cement paste or the cement particles, cement paste in between, and porosity. We all implement these things in our model. So this is a nano indenter where you indent with a needle, you get your low displacement curve, and from that curve we can get a hardness, which you can relate to strength, and we get the stiffness, the slope of the curve, which you can then have the stiffness of that position where you do the indent. And that's directly an input for the model. We do CT scanning. We saw already several images this week, and we will see more. They use that in the hospital to make 3D images of people, but you can also do that with materials to scan your samples, and then you get a 3D image of your sample. How it works is with X-ray. X-ray goes through the sample, and on the detector you see with grayscales actually the density of the material locally. So this is a CT scan of a small cylinder that we made, a concrete cylinder with spherical aggregates, which are low density, so plastic particles are this. So you see how they are distributed in the sample, and on the CT scan, this is one scan through the sample. You see all the particles actually projected on the screen. But then you rotate the sample a bit, do another scan, rotate again, another scan. And from all these scans, you can then calculate back with some software that you get with the machine, luckily. You can find back what the real image, a 3D image of your material is. So we can indeed do the test on different scales, but we still also need validation, because if we do only test, we have input parameters. So we can test the local properties of the cement paste by doing the nano indentation. We can also test, of course, our concrete cube. So we can have a compression strength, splitting strength, or tensile strength. We can scale up. The mortar we can do test. But we need the local properties, and we need validation of a test on a somewhat bigger scale. So we need tests at each scale to have the right properties. And for that, especially on this small scale, where we go to cement paste, and these are usually cubes of 100 micrometer. So this is 100 micrometer each size, which are quite small to do a test. So we developed a procedure to make cement paste particles of 100 micrometer, where we actually glue a block of cement paste on top of a glass substrate, and then start cutting and polishing it. The same way as Ozan told yesterday afternoon, how we make thin sections. But now we don't make them very thin, not up to 30 microns, but we just grind it off and polish it until we have a thickness of 100 micrometers. So we have a small plate of 100 micrometers on top of the glass substrate, and then we use a very precise diamond saw to cut actually in two directions. And then what we end up with are cubes on a glass plate of 100 micrometer in size. So then we can actually do tests on this very small cube. So this is how they look under the microscope, under an ESAM microscope. You see these cubes nicely sitting there, waiting to be loaded by your nano indenter. So here you see other image. So we can load them in different ways. We can use a flat indenter. So we load it, we compress it, and then we get the compression strength of such a small cube, or a prism in this case. So here, this one we loaded, not completely to failure, but you see cracking in this small prism. So that we can do, we can also use another type of loading, like the normal Berkovich indenter tip, which has this this shape. So we can push that in, and then you split actually your specimen open. So as I said, we do nano indentation to get the local faces of a cement base. So then we indent just a little bit to have the local strength and the local stiffness. But in this way, we can also get the strength of this cube of 100 micrometer that we actually simulate. And that was not easy to have such a test. And in this way, we are able to do it. So we can do indeed have the splitting with the Berkovich tip, which we can also scale up. We can go to larger scales and do the same. So we can make cement-based cubes and test that with other devices. So here the Berkovich tip is actually a diamond tip, which is quite costly to make. But with our normal install machine, we just use a steel tip. It's not that perfect, of course. A diamond tip is much harder. But with the steel tip, we could also damage the specimen and have the same kind of behavior and loading on a different scale. So we do then scales 40 millimeter, 20, 10 millimeter, and 0.1 millimeter. So that was the 100 micrometer cube. And we can look at the scale effect. We can look at all these curves and see how the size effect also is in there. And what we see, of course, is that the very small sizes have a much higher strength. So if you look at the hardness, then the 40 millimeter has a hardness of 0.2, then 20 millimeter 0.25, 10 millimeter we go to 0.37, let's say, and for the 0.1 millimeter, the 100 micrometer, we go to a hardness of 1. So it's much higher. It's somewhere over here. So you see that there's a huge size effect even on this material level that should be taken into consideration, because if you choose also finite elements or other elements to do simulations, then you have to implement the strength of the material at that size of the element, because that's the element that will fracture. So you have to also determine the strength on that size. So you cannot just say, I use finite elements that I simulate things on a meter scale, and I just use the same model to scale it down to millimeter or micrometer and use the same properties. Because there is a size effect in the properties, so you have to implement the right properties at the right scale. So then we can also do a splitting, of course, just like Brazilian splitting, but then only from one side with a tip. So this is a knife tip that we can put on the sample and we split it open. What we can do with this nano indenter, we can only measure up to the peak load, because after the peak we know that it will go somewhere like this. But this post-peak behavior, then you need a fast machine that it retracts and that it can decrease the load, but that's unfortunately not possible with the nano indenter. So we can only measure up to the peak, and then it will have a regime 2, which is a catastrophic failure. So here you see a lot of indents on cement base with water cement ratio. One is 0.3, 0.4, and 0.5 water cement ratio. And you also see that you have a lot of scatter. So you see all these curves give different values. What is scatter? That it's normal, because all the cement base are different. The cement particles, the stacking of the particles is different. porosity is different, so you should expect a great variation. So that's good, but you can take that into account in your simulation, of course. But then if you look to the average of the splitting strength for the cement paste, so then we see for water cement ratio 0.3, so which is the highest. So we reach 22 megapascal. So that's quite high for a splitting strength. On a normal cube, you have maybe 3. That's your strength that you will measure. 0.4 we go to 19, and 0.5 we go to 18. So that variation you find out nicely with this testing. Of course, you can put that in the model too. You can split also open these cubes, and if you do this for different microstructure, you will also find this variation, because if you use another microstructure as starting point, do the same test in your model, you will also find this huge variation that you find in the test. So here you see some of the simulations on 10 different microstructures for the splitting strength. So we see also we get a huge variation in strength, and in the model we are also able to get the post-peak behavior, because in the model we just can continue the simulation after we reach the peak. So let's see here, maybe C is the peak, or B, somewhere here in between is the peak. So then you see it's only partially cracked at B. But we can continue all the way up to D, and then we get this complete softening relation, which we cannot obtain in the test, but we can do in the model. So if we can make cubes, we can also make these nice prisms. It's even easier because you only have to cut in one direction. In this case, the thickness is a bit more. It's 400 micrometer or 500. We can make them. So then we have this cross section, 400 by 400, and a length of millimeters. I think 10 or 12 millimeters we make them. We can put them in a special clamp, like you see here. And this is actually the inside of a pencil. So because normal pencils, they have also the pencil itself is 0.5 millimeter. So that can clamp also on nice beams, but then they are very straight, and we can put this device in our CT scanner, and we can scan our sample at a very high resolution, because if you have samples of 0.5 millimeter, then you can get a resolution of 0.5 micron, and that is quite high, so you can clearly see what is in it. But we can also test these beams in 3-point bending. So we made a support, you see here. We put the micro beams in, and we can load them in a nano indenter. So here you see the support. Here you see our indenter tip, and we can load such a beam in 3-point bending. This is a camera that we can use to see what is happening during the event. So here you see 2 of the beams breaking. This one will also break in a minute. But you see it doesn't break slowly. We cannot control the specimen, the breakage. So it will break as a sudden failure, but we can get the peak load. And we did the same also for glass beams, because we knew that we have scatter in the cement paste. That's fine. But if we test another material like glass, we can also make these very thin samples and then test them, and then you see that we almost have no scatter, because glass is a quite nice material, which is quite homogeneous also. Also here we cannot have the post-peak behavior, but it should also be very brittle if we could measure it. But you see that the strength values and also the stiffness values, the scatter is not that much. And also these are similar to what is given in literature, so the values are correct that we get from these tests. So here you see again the 3-point bending on the cement paste beams, so of 0.5 millimeter cross section and 12 millimeter long, for 3 different water cement ratios. And here we also get, in this case, the bending strength, which is in the same order of magnitude as the splitting strength. But remember, the splitting was on cubes of 100 micrometer. So this here, the cross section is already 5 times larger. So you expect the strength to be a little bit lower because we have the size effect. And you see also these values are lower, and normally the bending strength is a little bit higher than the splitting strength. So we are in the right range we expect that it should have. So here you see a scan of such a beam, also after cracking. So you see here a crack in the material, and you see also the different constituents in the cement paste, the unhydrated cement, and the hydration products that you can clearly quantify. So then we do the multi-scale modeling. So we get the properties from a small cube that we can load in tension. Then we actually get this behavior. So this is the behavior if we simulate this small cube in tension. This is our load displacement curve that we get as output from this one. So locally the elements were brittle. So locally all the elements in this small cube, they only have this, then they break. The outcome of this simulation of the cube is a softening relation, like this. And then this relation we implement in each of the beams here. So this cube was actually 50 microns that we tested. And all the elements here are 50 microns long. So we give all these elements this behavior. So with the red dots, so a multilinear curve with 5 segments that we use as input. So now our elements are not locally brittle anymore, but all the elements follow this softening regime. Then we can simulate them. We get the strength. So we can compare that with the experimental values, and we see that they are nice in between the experimental values, so the simulation that we did. And the same for the modulus. Modulus is a little bit lower, but that's also what we expected. So we can do cement paste at different scales. That's nice. So the very small scale, a little bit higher scale of these small beams. But what is also important is the interface between our aggregates and our cement paste. Because that is the weakest link, as we also saw yesterday in the material. So we also need a way to test that interface. Because then nano-indentation might be quite difficult, because actually you want to pull on it and then measure the strength. So what we do then is we put cement paste on an aggregate in this case. So we don't use the glass plate, but just have the cement paste that we cast it on top of an aggregate. Then we take again our dicing, we polish it, then we take our dicing blade and in 2 directions, and then we see we have small prisms on top of our aggregate. They're sticking out. So we can cut again with the blade a little bit deeper. So then we have an aggregate with these cement paste prisms sticking out. So this is how they look under the microscope. So these prisms are 100 by 100 and 200 micrometer high that we then can also test. So you see here we place this sample in our nano-indenter, and we can just load it from the top where it sticks out here with our indenter tip, and it will break here. So it will break at the connection of the cement paste at the aggregate. And then we have, we don't have directly the strength, of course, but we have a measurement of the failure of the interface. And from so then we can again do inverse modeling to find back what the strength of the elements should be that we have in our model. So we also scan this sample in the CT scanner. So you see here the aggregate. This is our cement paste. And we can model this one with the element size that we have. So we put our three-dimensional lattice on top of it. And you also see that you have high porosity here at the interface. The blue one is our pores, so that's the porosity that we have there, which will create also the weaker interface there. Creates the weak connection. So that's why it will fail much easily here at the interface. So if we do the same in the model, we model the aggregate. This is our cement-based prism sticking out. So we load it here, and we can then choose some value for the interface element, because all these elements, we know the strength, we know the stiffness, but the connection here, so the connection between these two, that we don't know. And we can just fit it back in such a way that we have the same results for the experimental test, which are all these lines here, and the simulation. So this is the simulation, where we again can also have the post-peak regime. So we just fit them back by inverse modeling what the local interface properties should be, that we get the same strength values here. And then we have the interface properties. The interface properties that we can then use to simulate concrete on a somewhat higher scale, because then we have the cement paste, we have our aggregates, which we can just take linear elastic in this case, or we could also implement fracture in there, and we have our interface element, the purple one, which is the element around the aggregate, connecting the aggregate to the cement paste. And we have different input parameters. So we have a stress strain curve for cement paste, and we also have a stress strain curve for our interface, because that came from the previous simulations. And that is what we then put in. We can simulate the prism. We can make this same prism out of mortar or concrete, what is concrete with small aggregate particles. We can test that in tension or in compression and see how the crack propagates to the material by using the input parameters from the lower scale again. So we see fracture because we made two notches in the material, which you also see here. We loaded in tension in this case, and we see a crack propagating to the sample, but we also see that the interface is cracked. So all these black particles around the particle, the black lines, that are the cracked interfaces. So you see that you get local fracture here. You get actually a fracture zone before the crack localizes and opens like this. And here you see the low displacement curve of 3 tests, 3 experiments, and 3 simulations with different microstructures. So you see that they match quite well. So we both can have the maximum load and also the softening curve. They all fall in the same range. So we get these properties quite right by measuring the local properties of the cement paste, doing simulations there to a somewhat larger scale of the cement paste, measuring the interface between the aggregate and the cement paste, getting the properties of the interface from inverse modeling, putting all these properties inside a cube, and then we can nicely simulate what is happening in the cube on a larger scale. So this is an example of how we do multi-scale modeling from all the smaller scale of cement base, of the micrometer scale, up to the centimeter scale in this case, and we can take this one again to a larger scale to go to larger aggregates and do the same. So that's the same principle. And of course, you can do the same for self-healing. Eh? So if you have properties, capsules, or other particles where you put healing agent in, so you can also implement them in a model and study how they fracture. Put the interface properties of those particles in and see how that affects your fracture mechanisms and see what kind of crack risk you get. So you can play with the model to design your self-healing material. We also want to model fiber concrete. Now, yesterday already presented a little bit on this, so I can do this fast. So if you want to put fibers inside our cement paste, we just implement extra elements in our network. So the yellow one is our network of cement paste. And then these red elements that are fibers, which we connect to the cement matrix by some interface elements, so these dashed lines. So we have some extra nodes in the fiber that we connected together with an interface element. Then we need properties, of course, of the fibers and of this interface. Well, the fiber is easy because we can just do a tensile test on it, pull it, and we get the strength of the fiber and the stiffness. But especially this connection, these interface elements, what do we have to put in there? That's not easy. So what we can do is do the same pull-out test. So we can measure that with a pull-out test, so you get the strength and the stiffness of your interface. But we can do the same on the computer. We just make a small sample. We have the fiber inside, the green one, which is connected by small interface elements. And we just do on the computer also a pull-out test, and we get a low displacement curve. And then we just fit back what the properties of the interface should be. Just playing a little bit, change the properties, and then you will see, well, this curve will go like this, or this curve will go like this. And just play a little bit that is exactly the same as in your experiment that you do on the pull-out, and then you have the right properties of the interface. And if you do that for the fiber that you are interested in, so you can then look at distributions of fibers in your matrix. You can play with the volume of the fibers, so a small amount or a bigger amount of fibers. You can play with the strength of the fibers, with the stiffness. You can also align the fibers that they're all in this direction in your matrix. Maybe if you print something from a 3D printer, maybe they are more aligned than when you cast them or mix them properly. So you can play with that and then see what the effect of that is on a fracture test. So here we have a small prism that we then have the fibers in. We load it in tension, we just pull on it, and we want to see how they fracture. Actually, this is the prism without any. Oops, that went too fast. This is the prism without any fibers. This is with a small amount of fibers. So it was, I think, 0.5%. So here we go to 1% fibers, and this is 2% fibers. And you see, if you have no fibers, you get only one crack plane. So if you put on this prism, you get one crack plane here with some microcracks, because it's still a heterogeneous material, so you have some microcracks at other locations. If you increase the percentage, so let's say to 1% of fibers, then you have still one crack plane, but it's very wide. So you have microcracks around the main crack. So that is what this is. But if you go to a higher percentage of fibers, in this case 2%, so you get multiple crack planes. So you have one crack plane here, one here, one here, one here. And if you continue, you get more. And then you actually, oops, now I have to, well, you have a lot of red lines now. See if I can erase them. Oh, they are gone. So what you do then, if you pull this sample, so you have to load displacement. So with increasing deformation, you also see that the load will increase slowly, and your crack planes will be more and more. So this is like this bendable concrete, this ECC or SHCC, where you have when you get the multiple cracking due to the fibers that are bridging the small cracks. And if one crack is created, then you have to increase the load, and at another place your cement matrix will crack again, and there the fibers will take over, and you increase further, and the next crack will form, so you have this strain hardening material by this. And again, you can play with the fiber properties and see what then the effect is. So that's the beauty of such a model. So here, but you can also apply it for tests. That's what Dana also showed us. Here you see that fractures like this. It's not simulated. You see here the space. We don't have fibers in the material, but we have rebars, which are actually just big fibers. They do the same. They distribute the cracking. Also, cracking that develops in this material. Finally, here, the kind of shear crack developing in the material. And then she varied what she also showed yesterday, the H/D ratio, and then you see that you get the different crack patterns for these different simulations. Pen back. Yeah. So then you get different crack patterns when you change this H/D ratio. Yeah, so that was my final slide actually. I just have one question for the project that you have to work on for your swimming pools, and then you should just think about how modeling of fracture or other type of modeling can help you to design your lab experiments, and how you can also use these models to simulate the long-term behavior in your applications. So for the long-term behavior, then that's something that Branko and Claudia will touch upon, about diffusion, which you can also do with these models, or the self-healing tools that Claudia will present that you can also do with such kind of discrete modeling. So I will leave it up to here, but there is still time to answer questions. So I don't know if you have already some for me. I see that there are also some in the Q&A. Who starts with questions?
Excuse me.
Yeah, see you.
And determining the behavior of the interface.
Mm-hmm.
Well, it seems that in the imposed loading, it's kind of the shear, and we determine the strain shear, but how we transfer into it to the stress and strain. I think that as we
so this one.
Yes, the experiment actually.
Yeah, this is, well, I would say it's not shear, because this is how we load it.
Mm.
So we load it with the indenter on the small beam that is a cantilever, and we load it really at the edge, so it will just break here. So it's more like a bending behavior, and maybe completely at the end you have some shear stresses, but it's a fairly long beam, so it's more bending than shear. What indeed, you are right, there will be some shear also inside, but that will be transferred also to here. If you have shear stresses there, they will end up here as tensile stresses in the elements, and that will cause the failure. So yeah, but since our elements only fail on a tangent, so that's our criteria, that's how we implement it, and we just fit back what the properties are of this interface, because we don't know what kind of strength to put in of the single elements, because we that's what we do then here. All these single elements that are across the interface, they have a certain strength, but we don't know what they should be. So that's what we fit back from the test. So we do the test, we put some value in as interface strength, and then we see that we get the same maximum load. the same in the test as in the simulation. And then we say, well, that's the correct strength of the interface. So that's what we should use. That's how we do it.
Thank you.
More questions?
Yeah. Is there a specific modeling software you recommend using, like Abacus or Risa?
Yeah, that depends on what you want to model. If you want to model with finite elements on a somewhat larger scale, then there are several softwares that you can apply, Abacus or ANSYS or Diana, which simulates fracture. They all have fracture models in their tools, so you can use them. And you can also model diffusion with them and couple that, diffusion and fracture. Which one is the best for concrete? I don't know on that scale. I don't dare to say that.
Okay.
But what we use is a discrete element approach. So this is a tool that we developed ourselves. And for fracture, this seems to be quite good. It gives quite good results, and it's easy. So we prefer to use our own model, yeah, which you can use, but we're trying to make it as a tool that can also be used by others. But we are not there yet, because then you also have to write manuals and do it in a proper way that you cannot make mistakes when you put the input. So yeah, we are working on that to make it such that everybody can use it. If somebody of you wants to use it now, then we recommend that you stay some time in Delft and that we teach you how to do it, because that's quite difficult to do that online, to tell you all the tricks that you have to do to do a simulation. But that's possible, and I think Sina will follow that route at some point.
Thanks.
Okay. Other questions? If not, then I would say we have 8 minutes break, and then Branko can take over. Are you here, Branko? I see you.
I am.
Yeah, okay.
You won't be able to see me because I turn off my camera. If you do, then there's something wrong.
No, I cannot see you. That's good.
Okay.
So then you continue in 8 minutes?
Yes.
3 o'clock? Okay. Then see you then. Okay, it's 3 o'clock. We are back. So I see Branko is back, and I see cameras going on. So everybody is waking up. We also have 40 attendees in the live stream. So Branko, the floor is yours to tell us everything about using these kind of models for diffusion and self-healing and other things. Floor is yours. Okay. Can you share your screen?
I will try. Can you hear me?
Yeah.
Okay. Let me see. Let me see. Just a moment, doesn't seem to find my PowerPoint. Let me try once again. Can you see my screen?
Yeah, I think so.
Yes.
Yeah.
I think I should. So it's probably not full screen now, is it?
No, not yet. No.
Is it now?
Now it is. Yeah.
Okay. Sorry, I'm not that handy with Teams, and it's a bit complicated, but I think now it's okay. So thank you very much, everyone. Thank you, Erik, for inviting me to give this presentation. Actually, in this part, I will talk mostly about modeling of transport in relatively general terms. And then Claudia will take over with some parts on especially water transport and self-healing. And then there I will also interrupt her, or after she is finished, talk to you briefly about some possibilities of modeling for self-healing. So this is a general outline of the first part of my talk. So I will give a brief introduction of some motivation and why we do what we do. I'll describe a bit the lattice transport model, because now we're focusing on the transport. In the previous hour, we focused on the mechanics. Then show some applications of this type of model, and finally give some summary and conclusion and perspective about this type of use of this type of models. And as usual, I've noticed in this event, please feel free to leave your comments and questions in the chat. So what are we trying to learn in this short lecture? To show the concept of using the lattice model, which is the model that you've just seen, that type of model for simulating transport phenomena, and finally also how to couple this with the mechanical analysis, because many transport phenomena causes mechanical damage in our materials, and the other way around. Mechanical damage influences the transport phenomena. So what can we do about this with this model? So looking at concrete, I think all of you are familiar with concrete to a large extent. It's a multi-scale material with heterogeneities and pores that span different length scales, from nanoscale all the way to the macro scale. Concrete is the porous. Concrete is multi-phase. If you look at cement paste, it has many phases, hydration phases, CSH, CH, different anhydrated particles, different pore sizes. On a higher scale, we also have aggregates. But what is also interesting and important about concrete, that it's prone to cracking. So here on the left-hand side, we see a CT scan of a mortar, where we see aggregates embedded in a mortar matrix and different sizes of pores. And on the right-hand side, we see some cementitious material which has been exposed to sulfate attack and therefore cracked. So these are two things that we need to keep in mind when it comes to concrete compared to other materials. It's porous, it's multi-phase, and it's prone to cracking. And why are we talking about this in terms of deterioration? We are interested in different deterioration mechanisms in concrete. Reinforcement corrosion, ASR, sulfate attack, carbonation. And what is common for all these deterioration mechanisms, that to a certain extent, all of them involve transport processes. Transport of water, of CO2, of sulfate ions, of chlorides. And this is why we are interested in studying transfer process in concrete. So as I said, water is involved in all of these deterioration mechanisms. And maybe to relate a bit to what Erik mentioned about mechanics, the transfer processes of water and different ions are influenced by the concrete material structure. If you look at the millimeter to centimeter scale, we call this the mesostructure, where we can distinguish between large aggregates and the mortar matrix. So if we want to see how this affects the transfer processes, we need to look at what we call a mesoscale. So this is a scale where we can distinguish, I don't know if you can see my mouse, we can distinguish between aggregates, which are generally not porous, and the matrix through which, where the pores are and through which the moisture transport takes place. So here we have this guy, which signifies the moisture, and he needs to go around these impermeable aggregates in order to penetrate the concrete. And why this is important is because, for example, for reinforcement corrosion, we're interested in a very thin layer, which is our concrete cover, and which protects the reinforcement. And we need to see how different impermeable inclusions influence transport in this cover zone. So going to our lattice transport model, what is it? So Erik introduced the lattice fracture model, which is shown here on the top, where we discretize our material as a set of typically beam elements that can transfer forces, normal forces, shear forces, and bending moments, and we need to give them some sort of a constitutive relation, because we are going to expose it to forces or to displacement and then damage. Now, transport is similar and to a certain extent more simpler, because we, instead of discretizing a material as a set of beams, we discretize it as a set of pipes. And through these pipes, which are conductive, have 2 degrees of freedom, 1 degree of freedom, which is a scalar variable at the end. And when we connect these pipes in a 3-dimensional space, we can have a 3-dimensional transport model. So we, as is shown here, this guy is connecting pipes, and transport is going through 1-dimensional pipes in a 3-dimensional domain. So we simply use 1D elements to discretize a 3-dimensional space. So how does that work? Claudia will go a bit more in detail on this, but how we basically discretize our material, we start from a piece of material shown here, and we divide it into small boxes, small cubes. And that also allows us that to, if we want to, couple that to our CT scan or to some sort of material structure that we can map on it, because typically CT scan or our photos have pixels or voxels, which are small subsets of our image. So we do the same with our material. And then within each pixel, we define a subpixel, similar to what Erik showed for the mechanical properties. And within this subpixel, we position a node. Then we partition the domain. So we have these nodes that are then define our domain. We partition the domain using Voronoi tessellation, which is a certain type of mathematical operation that defines space that is closest to each node. So each of these colorful cells is closer to a node than to any other node. So there is a node in each of these cells. And that's very important for us, because we will use this knowledge to define cross-sectional areas of our transport elements. Then we also use these nodes to use Delanoid triangulation. So that defines the connectivity of our nodes. So then we connect our nodes into a mesh. So we start from nodes and we end up with a mesh, which is similar to what Erik showed. In this case, we have pipes. These are our pipes that will be used to simulate transport. So here we have a grid, we have a node, and we have lattice elements. And this is actually very interesting that the Voronoi tessellation, shown here in blue, is dual to the Delanoid triangulation. So there is, for each node, there is one Voronoi cell, and for each element, there is a facet of a Voronoi cell that corresponds to it. And we use this facet to define the cross-sectional area of each lattice element. So this is shown here in 2D because it's easier to visualize, but this is what we actually do in 3D. We have the Voronoi tessellation, Delanoid triangulation, and they're dual. They're mathematically dual. Then, because we want to look at the material scale, we want to implement heterogeneity. So there are 3 ways we can do this. First is to create a simple material structure based on our particle size distribution and assuming that our aggregates are spherical particles. So we have a simple algorithm that packs first the largest particles and then, according to the particle size, packs smaller particles. And we map that on top of our lattice. A second approach is to use a more complex packing algorithm, for example, an A&M material model that also Erik briefly introduced, in which we can pack realistic shaped particles into our domain. And then the same way we map this onto our lattice, and we can have aggregates, we can have the matrix, and we can have the interface. Finally, if we really want to use a real material structure, we can use a CT scan and then map that onto our lattice and use that as basis for our simulations. So the simplest way we do that is we have the elements that are within an aggregate particle, we assign with properties of an aggregate. Elements that are within the mortar matrix, we assign them with properties of a mortar. And elements that are in between, we call them the interface elements, we assign them with properties of the interface. So by simply assigning different transport properties to different elements, we are able to simulate the multi-phase nature of this of our material. And then we have the properties, we have the material structure. So now we have to define what type of process we are simulating. So far we have been simulating mostly diffusion type processes, which have a partial differential equation that's governing of this type. When we have an unknown quantity, theta, which can be chloride content, water content, temperature, and so on, a transport property, diffusivity, thermal diffusivity, conductivity, or so on, and it's related to time and space. In principle, we can solve other types of problems such as convection diffusion, reaction diffusion, advection, and so on, but we will mainly focus, in my talk at least, at the simple diffusion process. Claudia will go a bit in more detail in more complex processes. So, okay, so now we have our partial differential equation. We can discretize it using the standard Galerkin method, and this is our partial differential equation discretized in space. So we have a mass matrix, we have a time derivative of our unknown quantity, we have the stiffness matrix, again our unknown quantity, and we have the forcing vector. If you do the math behind this, you follow the Galerkin procedure, you will end up with elemental matrices of this form. And then we still need to discretize the system in space, in time, sorry. And for this, we use also a standard Crank-Nicolson procedure, and we end up with an equation of this type, where we can always calculate the quantity of our unknown quantity based on the previous time step. So we recursively do this procedure in order to calculate our quantity in each time step. And this is on an element level. On a system level, we do a standard finite element assemblage procedure in order to assemble the system matrices, which in our case, because we have relatively a lot of elements, can be quite large. So then we have assembled our system. We have applied the boundary condition. We have actually defined everything we need to perform our simulation. So now we are ready to use our models for different purposes. So I will show now some applications that we have used our model for, because every application also has some peculiarities, and then we will go through them in a bit more detail. So the first problem that we tackled with this approach was chloride diffusion. So this is a very important problem for us in civil engineering and in concrete materials, because chlorides penetrate our concrete, and then once a sufficient amount of chloride reaches the rebar will begin to corrode, expand, and cause cracking of the concrete cover. So we are actually interested in trying to have as impermeable cover as possible in order to delay the onset of corrosion and thereby extend the service life. So this process of chloride diffusion in a saturated condition is commonly simulated using a fixed second law, as shown here. And for that, as I said, we assume water saturated condition. And if you have a specimen or a piece of material that's underwater, this is correct. And also in practice, this is mostly used because it's relatively simple compared to other problems. So we assume water saturated condition in these simulations. Now, going back to our concrete, we have here a piece of material with areas in it. So we have a mortar matrix, we have areas, we have the interfaces. And actually, as I said, we need to know the transport properties of these parts. Typically, in experiments, you measure only the diffusion coefficient of your concrete. But for doing a simulation in the mesoscale, you need to know the diffusion coefficient of the individual faces. So in this paper, we actually done it by using the inverse analysis, where a lot of experiments have been used to calibrate based on analytical formulation to calibrate the transport properties of the mortar and the interface. Aggregate we assume as impermeable, and we came to a conclusion that for our model, the interface should have more or less 3 to 5 times more higher diffusion compared to the matrix. And then we can plug this into our model and see how that affects. So we tested it first on a simple case of uncracked concrete, and we knew how much aggregate there was. And if we simulate it as homogeneous material, we have this black line, very simple diffusion profile. And if we simulate it as a heterogeneous material, we have points all over the place, because actually in a real concrete, we don't have a sharp front of chloride penetration. We have a front that is more similar to what we've shown here, because aggregates are impermeable, so have zero chloride content. And we have an advanced chloride profile around the aggregates, because the ITZ is more diffusive compared to the matrix. And actually, in reality, we have a bit more complex problem than if we assume a homogeneous material, which is actually similar to what you saw in case of fracture. If you take into account the heterogeneity of the material, you will see more complexities than by simplifying it as a homogeneous material. Now, my interest actually during my PhD was more into investigating how cracks in the concrete will influence the chloride transport. So I focused on introducing also cracks in the material. And transport properties of cracks are not necessarily known. So what I did is I tried to simulate very simple experiments in order to try to inversely calculate the transport properties of a crack. So I found a set of materials that were performed by a group of authors on brick specimens, and assuming that the crack is the same in a brick or in mortar, try to simulate the cracks in a brick and back calculate the diffusivity of cracks. And then use those diffusion properties to simulate the same experiment on mortar, because mortar is more complex. In bricks, we don't have any interaction between the chlorides and the matrix. In cementitious materials, there is a process called chloride binding, which effectively diminishes the penetration of chloride in the concrete. So trying to simulate first the simple case, use that, and then go to the more complex case. So in cracked mortar, I used knowledge from the brick. So this is what came out of the brick experiment. So there is a relation between the crack width and the diffusivity of chloride. So the higher the crack width, of course, you have more diffusivity in the crack. And then we tried to use that to simulate the same in the mortar. But turned out that in the mortar, this type of cracks of diffusivity actually highly overestimates what happens. And this is probably because in the brick experiment, the specimens were not completely saturated. And if your specimen is not completely saturated, you have a very fast penetration of moisture, as you will see also in Claudia's presentation, because of capillary suction, because cracks are normally very small, and then very quickly they imbibe moisture. And with this moisture, chloride comes in at a much higher pace. But if you really saturate your experiment, your specimen, the chlorides penetrate into the diffusion only, and that's a much slower process. So actually, what I needed to do is I needed to recalibrate my cracks in order to get good results. So in literature, this has already been proven. So what you need to do is you need to be careful. If you perform experiments, you need to be careful that you do everything what you want to do, because the assumptions of your experiments need to be correct. And the same goes for models. If you assume something, the assumptions must be valid. You need to make sure that they are valid. So if you assume a saturated condition in your experiment and you want to validate your model, the specimen actually needs to be saturated, because otherwise you will have problems that are not related only to the model, but also to your experiment. So with this, we went to another set of experiments where we simulated specimens cracked in 4-point bending with different crack widths. And this is our experiment, actually experiments from this paper. And this is the simulation. So we see that the wider the crack is, the more chloride penetration we have, roughly. There is not a one-to-one correlation between the experiment and the simulation, because the experiment was a bit more complex than what we could simulate at the time. But in principle, we were able to show that there is an effect of cracks, and the crack widths, the wider cracks have more effect on the chloride penetration compared to narrow cracks. So this is already sort of a coupled problem, and we'll go a bit more detail in coupled problems later on. So we had, in this case, to perform first the fracture simulation, in which we define the crack and there perform simulation of chloride transport to simulate how the crack affects the chloride penetration. So now I have a question that you might want to think about and maybe share your thoughts in the chat. So if we are looking into chloride penetration, what is the role of self-healing of chloride penetration in cracks, and how can we model this depending on the self-healing mechanism? So we have a crack, and then we want to self-heal this crack because we don't want chloride to come in. So how can we do that, and what is the role of self-healing in this process? So please think about it and share your thoughts. Just a disclaimer, I have not done simulation on this, so any answer is valid and it will raise hopefully discussion. So another process that we simulated was a process of rapid chloride migration. So as I said, in the first part of our development, we simulated chloride diffusion, in which chlorides move under a concentration gradient. But this process is slow. It's relatively slow in nature. Actually, in practice, it takes years for chlorides to penetrate the steel. So commonly, in practice, if you want to characterize how good your concrete is in terms of chloride transport, you use an accelerated experiment, which is called the rapid chloride migration experiment. In this experiment, you apply a potential difference in the specimen, and because of the negative electrical charge of the chloride ions, they're repelled by a negative plate here, which is called connected to a negative voltage, and they're pressed into your specimen. So in this case, doing a simple experiment such as this will allow you to estimate the resistance of your specimen to chloride penetration in a matter of hours instead of days, months, or even years. So this is a standardized experiment within the Nordic standard NT-Build 492. And actually, you don't have only diffusion in this case, you also have ionic migration. So we want to see if our model can be extended to simulate that. So this is the governing equation of this process. We have chlorides, we have the diffusion coefficient, and this is our diffusion term, and this is the migration term, which as one of the parameters, it has the voltage difference, the potential difference. And the higher the voltage we apply, the faster the chlorides will penetrate into our specimen. So for this problem, there is an analytical solution that Tang and Nilsson have derived in the early 90s. And if we simulate that, we can also use this analytical solution to see how well our model performs. However, the problem is that this second part can cause some problems in the numerical solution, because in this case, the ionic migration is much faster than diffusion. So if you use the same discretization procedure, this will cause some problems. So as I said, in the previous problem, we used the standard Galerkin approach to discretize the equation. In this case, there is some problem in the numerical solution if you use this approach. So we used a somewhat more complex approximation with a characteristic Galerkin scheme, and then we get a bit more complex equation. But still, once it is discretized, you can simply implement it and see how it works. So the first test we did to see, we have going through the same procedure, we have implemented this equation into our numerical model, and then tried to test it with a simple 1D specimen, 10 by 10 by 50 mortar bar, and assuming these parameters. So the temperature is about 20 degrees, this is the voltage, and this is the diffusion coefficient. And actually, we see that our numerical solution sort of matches the analytical solution, but there is some numerical noise in here. So we thought we were on the right track, but we needed to look a bit more detail into this and see why this is the case. Why do we have this numerical noise? Because our models should actually show very good performance. And then we try to play with the element size. So we start from an element size, different element sizes. 1 millimeter, we have small elements, 0.5, 0.25, and 0.1 millimeter. And we noticed that the finer our mesh, the less noise we have, and actually the better the performance. So there is some mesh size dependency in this problem, at least in our implementation of this problem. And then we thought, why? Because normally for transport processes, for our diffusion type problems, we don't have any mesh size dependency. So then we wanted to look a bit into more detail why this is the case. And actually, if you look a bit into the fluid mechanics, there is a concept of a Peclet number, which is a ratio of the rate of advection of a physical quantity to the rate of diffusion. And for our problem, this number is defined as this. So it's related to the element size. So H here is the element size. So the higher the element size in the direction of the electrical field, to be honest, in this case, because we have a one-dimensional electrical field, the higher this number. And the higher this number, the more problems we can have in our numerical solution. So actually, we realized that there is a linear relationship between the voltage applied and this Peclet number. And also, there is a relationship between the mesh size and this Peclet number. So our error actually increases for a constant mesh size. The error in the solution increases the higher the voltage applied. So what we can do is we can select the finer mesh, or we can simulate lower voltage. So the higher the voltage you apply, we actually need a more fine mesh in order to get a reasonable solution. So once we realized that, we could also simulate some experiments. These are experiments performed at the University of Ghent, where they have actually introduced an artificial crack of different widths, and then exposed the specimen to rapid chloride migration for different periods of time. And then you see that actually the penetration of the chloride is quite enhanced in front of the notch tip, but it's not as wide as a diffusion profile. And this is also what we see in the experiments here. So this model was also able to reproduce these experiments quite nicely. And then we wanted to see what happens if we have a heterogeneous material. So we introduced aggregates again, we introduced interfaces, and with two different voltages, we can see two different behaviors. So we can really nicely see this front of chloride around the aggregates, because you will also see that if you do an experiment, an RCM experiment, and you cut your concrete, there is no the color of your silver nitrate solution will not change in your aggregates, and you will have a non-uniform profile if you use concrete. If you use mortar, you will have a very uniform profile. So this is exactly what we were able to achieve with the model. So this is a nice example of something that you could do with a model that is on a material scale. So another problem that we wanted to simulate with this type of model is heat transfer. So I think most of you are familiar with the process of hydration of cement. So it's an exothermic process, and in concrete, temperature will typically rise due to chemical reactions involved in the cement hydration. And for specific applications, such as, for example, shown here, we have a slab that is cast and then hardened. And after that, if we cast on top of it a wall, the movement of this wall will be restrained. And in practice, this is a big problem because this can cause cracking of this wall. And this is simply because of hydration of a relatively massive concrete here. So we want to be able to predict this rise in temperature in order to control that, because we can, in practice, apply cooling pipes, we can cool the aggregates, and we want to avoid cracking like this. So we want also maybe to see if there are material alterations that we could use in order to reduce the temperature rise in this type of structure. So if you go back to our diffusion type equation, this is the equation that is used typically to simulate heat transfer in the material. We have conductivity, we have the heat capacity, we have the density of our material. But in a hydrating concrete, we also have heat that is being generated. So some new heat is occurring in our material, and it's related to the rate of heat production due to hydration. And in our model, actually, we implement this by heat generation in each node of our model. And this rate also is related to the volume of each Voronoi cell that we have in our mesh. So this is, in this problem, an additional term compared to the other problems that we have seen so far. So we then want to see if our model is doing what we want it to do. We implement a heat production rate from isothermal calorimetry. We implement that into our lattice. This is a very simple homogeneous mesh, and we implement these heat production rate in each node of this lattice and compare that to an analytical solution of this problem. So we have a thermodynamic solution shown here in black, sorry, in red, and our model shown here in black, and they match perfectly. So that means that our model is able to reproduce this type of behavior in itself. So it will not cause any numerical error by itself. So then we wanted to use this model to simulate a specific additive that we were looking into that would be used to limit the temperature rise in concrete. So some of you might be familiar with the concept of phase change materials. Phase change materials are combined latent, and they're able to store heat. So if you heat up a phase change material, it will turn from solid to liquid, and during the process of changing from solid to liquid, it will absorb a lot of heat, and vice versa. So once it goes from liquid to solid, it will release this heat. So it is able to absorb this energy, and the idea was that in concrete, absorbing this heat will prevent the concrete from heating up too much, and eventually cracking, this type of problems. So typical phase change materials is a candle. So once you heat up a candle, your wax will melt, but at this melting temperature, it will store some heat, and the other way around. So the idea was that we were to implement these types of materials in concrete in forms of microcapsules. So similar to some of you might be familiar with microcapsules with encapsulated self-healing agents. In this case, we had paraffin wax encapsulated and added to concrete as additive in order to absorb and release heat in concrete. So then we wanted to simulate this with our lattice model and see how different amounts of these type of microcapsules would affect the heat rise in our material. So the heat transfer is actually the phase change. It's a very complex process. What we decided, we simulate this using a latent heat capacity method. So actually, the phase change is simulated by changing the heat capacity depending on the temperature. So we have a temperature-dependent heat capacity, and we have here also the temperature phase change, because you can tailor these materials to have a phase change at a certain temperature depending on what you want to use in your applications. For example, for massive concrete, you want probably to have a phase change about 30 to 40 degrees. And then we play with the parameters here to see which type of material we would want to have in our concrete. And that is actually a nice thing about models, because with a model you can play with the parameters and then go back to the lab and see if you can actually make the materials with such parameters that you know will work for your application. Because otherwise, sometimes there's a lot of trial and error involved in material development. So we simulate an adiabatic heat rise in cement paste. So in black here we have a pure cement paste. We have then cement paste with 10% of PCM, 20% of PCM, and 30% of PCM. And we see that the higher the percent of our phase change material, we are able to actually delay the onset of temperature change, because in this case, we took a PCM with temperature change at 24 degrees. And as the material starts heating up from room temperature to 24 degrees, it's actually, if you have a phase change material, it starts absorbing the heat. So the overall material stops heating up. And then you're able to delay the onset of temperature rise if you wish with these type of materials. Also, different types of phase change material, different types of waxes have different capacity for storing the heat. And then again, if we increase the heat storage capacity of these materials, we're able to delay this even further. And also, if you increase the amount of phase change material, you're able to delay this further. So this type of tool can allow us to design and tailor PCM-based composites to minimize thermal cracking, because we can take this further to our structural model and see actually how this affects the cracking of our structure. And then we can go back to our material and change it and adjust it the way we need it. So I was thinking about this type of problem. I know that you are all busy with different self-healing mechanisms, and I was thinking, well, if we think about self-healing, which type of self-healing mechanism can we use and further develop to control early age cracking in concrete, and why? So think about vascular systems, think about bacteria-based systems, think about SAP, think about encapsulated adhesives, and so on. So specifically for early age cracking, and maybe even more specifically for high performance materials, for high performance concrete with low water cement ratio, what should we look into, and what has promising properties that we want to use in this type of application? So maybe if you have an idea, please share it in the chat and we can discuss that further. Let me see what the time is. Okay. Let's continue. So I will here summarize this part of my talk. So we have shown that the transport lattice model is an effective and versatile tool for modeling transport processes in heterogeneous materials. So you have applied it so far for different types of problems: chloride transport, moisture transport. You will see that in a bit with Claudia. Heat transport on a material scale. So as I said, we can quite easily implement material heterogeneity, also similar to what Erik showed about the fracture simulations. We can also do that in terms of transport. What is also very nice is that the model is compatible with the fracture lattice model and can be coupled if needed. So what I've shown so far was coupling between cracking and chloride. So Erik showed you how to simulate cracking. You can then use that output of that model to couple it with chloride. Cracking with moisture, we will go into this in a bit. How to couple cracking and moisture to simulate, for example, shrinkage. And what is also nice about the model, it can be used in different length scales. So you just need different input, but the modeling tools are in principle the same. You can use it on a micro scale, you can use it on a mesoscale, you can use it on a macro scale. So this is very nice and shows the versatility of this model. So what are we looking into the future? We have only scratched the surface of potential of this model. So we can also look at other degradation mechanisms, for example, carbonation. Claudia will talk about that, but other mechanisms as well: sulfate attack, delayed atrograph formation, and so on. Furthermore, so far we have looked into single ionic diffusion, but in a concrete pore solution, you actually have many ions that act and they interact due to different charges. So we might want to look into that in the future. Other materials, so we are looked into concrete, mortar, cement paste, but in principle the model is applicable to any porous material. So maybe we can use it also for other materials as well. Also for self-healing materials and designing these materials, Claudia will show also some uses of this in a little bit, but still developments are possible. So in the end, there is still plenty to do in using these type of materials for designing new materials. Let me see, is it maybe nice to have a break now? Because is Erik here?
Yes, I'm here.
Do you think we should have a break now? Maybe 10 minutes, because I think I have about 15-20 minutes more, but maybe it's better to have a break now and then continue.
Yeah, that's good. Let's have a small break.
Yeah, maybe 10 minutes. Not so we continue 10 to 4.
Yeah. Okay. Good.
I'll try to see if there are any questions. Minfei has a question. how the effect of self-healing can be reflected on the rehabilitation of microcracks inside the numerical specimen. Actually, that was the same question that I had. So I would prefer an answer than a question. If you have any idea, because this is not something that is solved. Actually, Claudia will show you one approach for her problem, but this is something that requires different ideas depending on different self-healing mechanisms. So it would be nice to hear some suggestions, or at least you can think about that for your own purposes. I don't see any other questions.
No, I put them in published already, but most of them I answered.
Ah, okay. Actually, I don't know how to, because I have an option of replying, but I think it's if I reply, then it's to one person.
No, I think to anyone.
Okay.
Now they are in published, and then you can answer.
So Wavi has a good question. Claudia should have an answer.
Last one.
Second to last.
Hi everybody. Sorry that my webcam is not working. I fixed it yesterday somehow, but today it's not working anymore. So I guess it will be like a podcast.
Oh, that's fine. If you can hear you and see the slides.
Yes. So to Wavi, is that how it's pronounced? So you ask how to take into account the kinetics of the bacteria. So I will, as Branko mentioned, present an approach that I use for modeling of crack self-sealing with superabsorbent polymers. Regarding how to, actually, sorry, this is an answer to the question from Min Fei. I will go back to Wavi later. So how the effect of self-healing can be reflected on the rehabilitation of microcracks inside the numerical specimen. So actually, I did some modeling on the crack self-sealing of mortar with superabsorbent polymers. And basically what I do is that I simulate the evolution in time of the superabsorbent polymer swelling, and then how elements that before were belonging to the crack space that had certain transport properties, once they are occupied by superabsorbent polymers, they become superabsorbent polymers elements with certain transport properties that will influence how, for example, if you are simulating, in my case, capillary absorption of water, how this, let's say, piece of crack that was a crack before but now is occupied by a healing agent, then how does it reflect on the transport in the crack? So this is, let's say, a way that you can do it as well. There are examples in literature in which you can use a more, let's say, average approach. So you, let's say, for example, reduce the porosity of a certain element if you have healing in that specific part of the domain, etc. But yeah, you will see more detail in my presentation. Regarding Wavi, I'm still myself struggling with it. You can, for example, what I'm doing is to monitor the healing of a section which is cracked. So I monitor it with microscopy, and then I try to backfit the model with this. So you can use the model actually to find this rate of bacteria activity rather than measuring it itself, which can be actually quite complicated. But of course, it would be nice at the end of the presentations to discuss different ideas, because yeah, I've been working on this for quite a while, and it's always nice to hear fresh approaches of people who is not, you know, set yet on how are they going to approach the problem. So I'm actually curious as well of if you come up with an idea or something after we have finished the presentations. If you like the podcast, please register.
Okay, we continue. So now we will go. I realize I probably made more slides than I have time to discuss, so some parts might be a bit quicker, but we'll go through three sort of different topics, discuss a bit about a couple problems, because we've discussed problems that you have transport. Then if you have the influence of cracking of transport, but how about the other way around, if your transport influences your cracks? Then we will look a bit into a process of reinforcement corrosion, which is actually more of a mechanical problem than a transport problem once the corrosion occurs. So it relates a bit to what Erik showed, and very quickly some overview of some ongoing projects where we are using or planning to use this type of models. So in terms of couple problems, I mentioned already, maybe hinted, that moisture transport could affect the response of our materials. So if you have drying of your surface, a gradient of relative humidity will occur that will cause stresses in your material, and because these stresses are it will cause strains, and because these strains are partially restrained, that will cause stresses, and these stresses may cause cracking in your material. So what we actually do is we perform a moisture transport simulation. So first we simulate the profile of moisture or water profile in our material. Then we perform a mechanical simulation in the way that Erik showed, and then we can simulate crack propagation in the cover. And this is simply related because the strains are related to the change in relative humidity through a coefficient alpha. So just quickly, because Claudia will go into more detail, we have again a diffusion type of equation, a bit more complex in this case than in case of chloride transport, because our diffusion coefficient here, for moisture, for relative humidity, is dependent on the relative humidity. So it's not a linear function. But in any case, the implementation is relatively similar to what we had so far for the chloride transport. But what we do here is use the output from lattice transport model, which is relative humidity at each node, to calculate the load in each lattice element according to the relation I showed in the previous slide. So this is how it looks in a simple way. We have an initial state with relative humidities at ends of our nodes. At a certain time, this relative humidity changes, and actually in our lattice, the change of the length of our model is restrained by actually the model itself. So we apply a shrinkage or expansion if we have an increase in humidity, and actually that will result in forces. So we actually apply a force in our lattice to simulate the humidity change induced strain difference. So first, as I said, we need to validate the model. We use a commercial software with certain properties. We apply drying at this site. We have a two-layer system, because actually the goal in this study was to simulate concrete repair. So we have a repair material, we have a concrete substrate. We simulate the same using a lattice model, just to check if the model does what we want it to do. So the first thing is to check the numerical implementation, although we have a model that does exactly the same. So this is not our final goal, but we want to check if everything is working okay. And actually, the model showed very good performance, so no difference between the commercial software and our implementation of the problem. But what we want to do actually with our model is to go further, to go to the material scale. So we added aggregates into the substrate, and these aggregates cause heterogeneous profile of moisture. We increase the diffusion coefficient of the interfaces, and actually turned out that although we showed that moisture transport and chloride transport are faster in the interface, also the drying is faster. So in both cases, the water going in and the water coming out of your material, it is influenced by the presence of aggregates and the presence of interfaces. And going to the coupling with a mechanical simulation, this faster drying will cause stress concentrations. And also we have different mechanical properties of the aggregates, of the interfaces. And this stress concentrations may cause cracking in this locally weak zone. So actually our model does what we wanted to do, and it's ready for us to use it for our study. So as I said, we are looking into drying shrinkage. So what we do is of repair materials. So what we do is we have a substrate, which you typically prepare by roughing it in practice with water jetting or sandblasting. So we have some exposed aggregates. You cast the repair material, which numerically is very easy to do. You expose it to drying by applying a certain relative humidity on the outside. And then you simulate the moisture transport. You use the output for simulating fracture, and then you get cracks in your material. So cracks in your repair material, sometimes depending on how good your interface is, these cracks penetrate into the substrate. And this is very similar to what happens in nature, not only in concrete, so here we see concrete, but also in other materials such as clay. If you have seen ever a soil in a desert area that is dry, this is what you can see, because there is a humidity profile and it's very dry on the outside. It's a bit more moisture on the inside. The movement of these two does not match, and that's why cracking occurs. So if we look into the bond strength, because of course when you cast the repair material, you need to have a certain bond between the repair material and the concrete substrate. Sometimes this bond is very strong, sometimes it is not, and depending on this, we will have different results. So we have a repair material here simulated of 10 millimeters. We will have cracks going at 90 degrees. So in this case, we applied, I think Erik has mentioned this, periodic boundary conditions. So we have periodic boundary conditions in two directions. If I look at from the top, vertical and horizontal. So actually, this crack continues here, and this crack continues here. So we can simulate cracks in this type of material, and by taking only a piece of material, using periodic boundary conditions, we are able to simulate a representative part of the material. If we add fibers, that's quite typically done in concrete repairs, because it's known that fibers limit the crack widths. Here we have a comparison of two same the repairs of the same thickness, same boundary conditions. This one does not have fibers, this one has fibers. And we can see that the addition of fibers actually causes a reduction of crack widths, but the increase of number of cracks. So you've also discussed yesterday and a bit today about SHCC or ECC. If you use that type of material, you will have more cracks, but narrower cracks. And this is most of the time preferred in repair applications. You don't want to have very large cracks. This you can also play with a bit by changing the thickness of the material, repair material. So by having a thinner repair material, you have also more cracks of smaller crack widths. Same boundary conditions, everything is the same, just a thinner repair material will typically have smaller cracks. Also, if you have increased bond strength, you can also get even more cracks for the same material thickness. And this is again seen in other types of materials as well. So very simple systems. You see that the crack orientations and the amount of cracks, but also the angles between these cracks, they change depending on the thickness of the repair material, because that thickness will actually define what is the gradient in your material. If you have a thick material, you have a very dry surface and moist inside. If you have a thin material, then your repair material is exposed to more or less the same moisture gradient, and then it's more uniformly stressed. So here we see again the influence of the thickness. 10 millimeters, we have more or less 90-degree angles of between these cracks. Thinner material, 120 degrees between the cracks. So that changes the pattern. you're able to play with this in the model, but this is also something more or less a trend that you will see in experiments and in practice. If you add fibers for 10 millimeter repair, you can have smaller cracks and more cracks, as we've discussed. And this is actually how it works. This is an experiment showing crack development. A picture is taken from the top of the material, and this is a simulation of the same. So you see actually how cracks occur. And because of the nature of the simulation, you can also make a surface a bit transparent. So you see here an aggregate from the substrate that also causes some stress concentration. So you can imagine that if you have a thin repair material, your aggregate, your local stress concentration will have much more effect than if you have a thick repair material. So surface preparation may have a much more important role in a thin repair compared to a thick repair, and this is also shown experimentally. So with a model, you can very easily vary these parameters, try to understand fundamentally how they affect your repair, and then use that to design your experiments and further on to design your repairs, for example, in practice. So going back to more mechanical problems, just shortly about corrosion of reinforcement. So I think most of you are familiar with the problem of corrosion of reinforcement in concrete, but it's a very important problem for reinforced concrete because it causes several problems, not just loss of steel cross section, because that's the easiest actually to measure, because you know if your reinforcement corrodes, your steel cross section decreases. But typically in reinforced concrete, when we design reinforced concrete beams or members, we have more steel than we need for low bearing capacity. So that's more or less not that big of a problem, at least in the beginning. However, a bond between steel and concrete can change, and that could be an important thing if corrosion occurs in the wrong place in your concrete element. Ductility of steel is changed because steel becomes more brittle. You have in steel that has some pits, there is more stress concentration, and the ductility of steel changes, and that's an important problem because actually steel is there to make your reinforced concrete element more ductile, and if the steel becomes more brittle, that's a problem. And finally, for reinforced concrete beams, it's possible to change the failure mode completely from shear failure to bond failure. And these are all very important aspects and why we are actually interested in reinforcement corrosion. Not corrosion per se, but how that affects the load bearing capacity of our structure. But there is a bright side to it. Actually, corrosion is a very common problem, but normally serious problems are caused by reinforcement corrosion. So all three problems here, number 2, 3, and 4, are typically preceded by cracking of the concrete cover. So actually, we already have a warning. If the concrete cover is cracked because of corrosion, typically if we do a visual inspection, we will see this. And if we take action on time, we will not have all of these other problems that I mentioned. So how does this process take place? We discussed in the first part the process of chloride diffusion. So chlorides will diffuse to the steel. Once corrosion is initiated, actually rust occupies a higher volume compared to the parent steel, so it will expand. But there is some porosity around the rebar, so we will have some expansion of rust before actually stressing the concrete. Once this is all filled, stresses will be initiated in the concrete, and once these stresses have reached and exceeded the tensile strength of concrete, we will have crack. It has also been shown that corrosion products tend to migrate into pores around the steel and open cracks. So actually, not all corrosion products cause expansion. So we want to take that into account in our model. So here we have a SEM image showing penetration of corrosion products into an open crack, and we want to see how that can be reflected in our model. So actually, the pressure that is caused by uniform corrosion, I will limit myself here to the case of uniform corrosion, is a function of many factors. Radius of the bar, how much steel has been lost in the process of corrosion, which you can sometimes measure. But some parameters that are not that well known, migration of corrosion products. As I said, corrosion products tend to dissolve in water and migrate into open pores and cracks. The density of corrosion products, that has not really been defined, and the Young's modulus of corrosion products. So these three especially are not that precisely quantified. And the pressure is also, sorry. So this is the pressure, but how much pressure you need to cause cracking is a function of also rebar position and the local mechanical properties of concrete. So depending on where your rebar is in your concrete, that will have an effect, but also the mechanical properties of the concrete. So we wanted to simulate this process using the lattice model as explained by Erik. And we found a very nice set of experiments published by Andrade in '93, where they simulated accelerated corrosion of specimens of 150 by 150 millimeters, and with three different positions of rebar. So corner rebar, middle rebar, and a middle rebar with somewhat thicker concrete cover. And we tried to simulate this first for one of the experiments, and this is the experimental result, and this is our simulation. So we have a relationship between the crack width and the exposure time. And actually it turned out that there is an influence of this porous zone. So we say there is a porous zone around the rebar, similar to the ITZ, that's able to accommodate corrosion products. So the bigger this porous zone, so these are the simulation lines. This is the black line is no porous zone, and the bigger this porous zone, the later the cracking will occur. But we see that actually, even taking that into account, there is no match between our simulations and the experiments. So although this delays the onset of damage, there is not good match between these two. So actually, we needed to take into account the penetration of rust into open cracks. So we can say that, for example, cracks larger than 25 microns allow penetration of cracks, or cracks larger than 50 microns, or cracks larger than 75 microns. Finally, cracks larger than 100 microns. And that will then change the slope of this curve. And actually, only by taking into account both the existence of the process zone and the penetration of rust into open cracks are we able to get a right trend in our model that corresponds to the experimental findings. So actually, penetration of rust influences the crack propagation kinetics, because it turns out that if you don't take it into account, you grossly underestimate the time to surface cracking and actually overestimate the crack width. So these are some simulation results. So with the corner bar, the middle bar, and middle bar with a higher concrete cover, and we have taken into account the material structure of the concrete. So actually, cracks penetrate normally through the ITZ and through the mortar, very rarely to the aggregate, because we have given aggregate a higher stiffness and a higher strength. But actually, we also, what we realized from this type of exercise is that in all cases, especially in cases with thick concrete cover, we have a lot of internal cracking preceding the surface cracking. So we have a crack penetrating to the surface, but in reality, that's already quite late. So we have a lot of internal damage before we can see that. So we should be careful with the interpretation of visual inspections. And I will not go into that in detail here, but if we also simulated the cases of pitting corrosion. In the case of pitting corrosion, we have even more internal damage before we have surface damage. And pitting corrosion is typical of chloride-induced corrosion, so it can be in some ways more dangerous than uniform corrosion, which is typically what happens in carbonation conditions. And then here I show different experiments and different simulations match quite well if we take into account the existence of the porous zone and we take into account the penetration of corrosion products into open cracks. So for different geometries, here where the rebar is positioned, we also need different amount of pressure to cause the cracking. And this amount of pressure is actually linearly related with the amount of corrosion. So how much steel has been corroded at that moment. So actually, this geometry needs more corrosion before it shows cracking compared to this geometry. This is a bit expected, but it also means that we need to be very careful with assessing what is acceptable. If we accept higher levels of corrosion, in this case, we already have damage. So be careful what we do in practice. So to conclude this small part of my talk, we can simulate corrosion-induced cracking using the Delft lattice model. The cracking patterns, I did not go into that in detail. We actually simulated each of these cases for different material structures, so we varied the distribution of aggregates. And that sort of influences the cracking patterns, but also to a certain extent, cracking pressure. So there's a bit of a statistical and a stochastic nature of this process. The initiation of cracking, actually the initiation of visible crack on the surface, is largely influenced by the existence of the porous layer around the steel. And the crack propagation, so the kinetics of how cracking propagates, is influenced by penetration of corrosion products into open cracks. Now, these two parameters are still largely under investigation in terms of experiments. So we, in this work, we have played with the numbers, but what really should be put here in the model is still not known. So we are hoping that in the future we will be able to understand these processes a bit more. And what I've not gone in detail in this part is that we also need to know the elastic properties of rust, and that is also largely unknown. So we're doing experiments to understand how elastic properties of rust are influenced with different parameters. For example, typically in lab conditions, we do accelerated corrosion experiments, but this is not quite representative of natural corrosion, of the rust that occurs in natural conditions. So we're trying to understand how these two can be correlated. So another question that I would like to hear from you about is that if we are going to use self-healing to close cracks in order to delay corrosion or minimize corrosion, should we focus on closing cracks before corrosion occurs or after corrosion starts, and why? And even more so, which tools do we have to do that? Which self-healing mechanisms can we apply in each of these cases? So please think about this. And finally, shortly about some ongoing projects, not all necessarily related to self-healing, but maybe of interest to at least some of you. So we are at the moment looking into the use of 3D printed reinforcement in cementitious materials. So some of you, or probably most of you, are familiar with the concept of 3D printing, where you use a computer design to make a three-dimensional object. And we are trying to use that to print reinforcement and use it in our mortar and see if that actually is something to investigate in the future. So we have developed simple reinforcement meshes for small specimens in the lab, and we have subjected these specimens to 4-point bending, to uniaxial tension, and try to see if we are able to get multiple cracking and strain hardening behavior, similar to what you get typically in SHEC, in ECC, because in that case, you can have very good materials for different purposes. And we were very interested in seeing if this we can achieve with 3D printed reinforcement. We also used our lattice model, as described by Erik, to simulate these processes. So we have different designs. This we call large triangles, small triangles, mixed triangles, and simulate the performance of this. So actually, we had quite some interesting results. For large triangles, we were not able to achieve multiple cracking or strain hardening. But for mixed triangles and small triangles in 4-point bending, we got multiple cracking, which was very interesting. And actually, the difference between these two cases is that this one has a dense mesh all over the specimen, and this one has a dense mesh only in the middle, where the maximum moment occurs. So this one actually has much less, MT has much less reinforcement compared to ST. So actually, it was very nice to see that we can actually save on reinforcement in this case. And experimentally, we also saw in uniaxial tension that the small triangle design has multiple cracking. So here we use the digital image correlation. I think you have seen some examples of DIC yesterday. so if we have large triangles, our mesh is pretty much pulled out after first or second crack occurs. So no multiple cracking. If we have small triangles, you have multiple cracking. So first we have 1 crack, 2 cracks, and we have a lot of cracks as the strain increases, and a very nice strain hardening behavior. And only in the end we have a pull out of the reinforcement. So this is quite promising for this type of application. So we are still in lab stage, but hopefully we will get some nice results and go a bit to a larger scale in the future. Another thing that we're looking into is using the lattice model to simulate the 3D printing of concrete. So this is a process of 3D printing where you deposit consecutive layers of concrete in an extrusion type process, and actually eventually your 3D print will fail depending on how you print, which type of material you use, and the geometry you use. So we want to be able to simulate that with a numerical model in order not to do trial and error procedures again. So just to understand how this occurs in experiments. And some applications in practice already known. So this is a very let's say booming field of research, and very interesting also for us, because we have also colleagues that do experiments on this. So we want to be able to help them as well. So in 3D printing of concrete, extrusion-based 3D printing of concrete, there are 2 typical failure mechanisms. One is plastic collapse, where the bottom layer cannot sustain the weight of the layers on top of it. So it yields and the material collapses because of this. Another failure mechanism is typically defined as elastic buckling. It's because a geometric nonlinearity occurs. We have second order effects, and the specimen on the print simply loses stability and fails, even though before that the material was perfectly able to carry the weight of the layers above that. So we want our model actually to be able to reproduce both of these and tell us how this will happen in our experiments and how to modify the material. So Zechang, he developed a model in which we are able to, as you see in this animation, add layers of material on top of each other that adds weight to our material. We have also implemented development of material properties because these materials are very young, so they hydrate. And then he is able to quantify actually how many layers of a material can be printed before failure, and finally also reproduce the failure. So here comparing his simulation results to experiments actually shows quite a nice correlation. Sorry. So. So he was also able to simulate a different type of experiment in which you have elastic buckling as a result. So here we have an experiment where you print a 3D printed wall by placing consecutive layers on top of each other, and you do the same in a simulation. And typically he was able to obtain the same failure mode as in the experiment. So we're still working on the model, but it's showing quite some promising results at the moment. And finally, the third project I wanted to introduce is probably the most related to your work, is use of 3D printing to create vascular networks for self-healing concrete. Z1 is a PhD candidate working on this. I saw that there's some similar research being done at the University of Cambridge, but 3D printing actually allows you to design and actually make a complex vascular structure and implement it into your material as a vehicle for injecting self-healing agents. And Ze is currently developing this, starting from a relatively simple structure shown here. But first experiments are quite promising. So he's able to inject low viscosity epoxy into the material and actually regain the water tightness, and to a certain extent some strength as well. So this is something that he's working quite hard on at the moment. So this was my last slide, and I would like to thank you for your attention. And if there are any questions, please post them in the chat, or at any time contact me using my email, and I will be happy to discuss. Thank you.
Okay, thank you very much, Branko.
Let me see if there are any.
Can also have questions here from the people in the room if they have.
Okay.
If there are burning questions now, just open your microphone and start shouting.
Oh, hi.
Hi.
I had a question.
Yes, I hear you.
Yeah. In real environment, when the agents from the environment go inside the concrete, they generally do not go only by diffusion. There are other mechanisms also involved in it. For example, convection and the capillary action.
Mm-hmm.
So I wanted to ask if you have tried to simulate those processes as well in your models.
So Claudia will discuss the capillary absorption problem. So that has been simulated, but we have not. So we've done that for water transport, but not yet how, because if you want to use it for example for chloride transport, you need to couple first you have the water transport and then the chlorides go in. So we've done that for water transport at the moment at Action. Yes.
Okay.
But Claudia will discuss that, I guess, in a bit.
Yeah. Okay. Thanks.
The problem with these type of mechanisms, if you look into for example for chloride, is the validation of the experiment. So you can it's done, it can be implemented, but how do you validate that? There was also a question here in the chat about chloride binding.
Yes.
I don't remember who asked that. That's very easy to put into the model. But getting the data on your chloride binding isotherm and validating that's not the easiest process in the world. It's quite time consuming, labor consuming.
Mm-hmm. Yeah. Thanks.
Other questions?
Not yet, I think. So there are some in the chat, so you can answer those. And,
I think this is for Claudia.
That's for Claudia already, okay. She didn't start even. So.
Yeah.
So you have both your presentations now. So Claudia will do the last one, if I'm correct.
I have actually a very short presentation on self-healing capsules.
Yeah. But you can do that at the end also.
Yeah, I'm thinking after Claudia is finished to do that.
So Claudia, do you need some break before you start? Or maybe the others need a break?
I'm fine, but maybe the attendees need a break, go to the toilet quickly, 5 minutes.
Yeah, so we can start at 4:30. So that's a nice time. But in the meantime, we can also try to make a group picture of all the people that are present. So then you should put your camera on. I think we can only have 9 at the same time. And maybe one of you can share the screen. So then I can also see it, because I don't see the same as you see. So I don't know. Who can share the screen? I see Tim is sharing. Okay. Yeah, that's what we want to see. So now we can all take group pictures. And can maybe now other people turn on the camera, and the one that has the camera on now can put it off. Okay, I think this worked. Did you all make pictures? So if you all make print screens, then Claire will put them somewhere on the internet or in the, I don't know where they go, but they will be live in a few seconds, I'm sure.
In any case, it was nice to see everyone's face pop up for a moment.
Yep, that was good. Okay, so a break till 4:30, and then Claudia will start. Okay, Claudia, I stop sharing, then you can share again. Can you also make it full screen in presentation mode?
Ah, there it is.
Perfect.
Okay, somehow it didn't work with the PPT, but with the PDF it works just fine.
Now we see Branko also. You can click him away.
Yes. Well, sorry that you cannot see me. Technology is not on my side today. Okay, well, welcome back also to me. I will be the last speaker. Well, Branko will intervene a little bit at the end of my presentation, but basically I will be talking about the last topic of our modeling lecture. Specifically, I will be talking a little bit about modeling of permeability and self-healing in cracked concrete through obviously lattice model, because we love it here in Delft. I left one discussion point on purpose at the beginning, even though it would be nice to discuss it at the end of the presentation. But actually, we already started this discussion. Basically, I was curious to know which of you already foresee the use of mass transport modeling or even fracture modeling in your PhD project, and whether we could discuss a little bit of which are your thoughts. I know that most of you just started your PhD project, but it is always nice to hear ideas or to at least fantasize about what could be done. But let's leave it for the end of the presentation. I will start my presentation with this first part by talking about lattice modeling of moisture transport in sound and cracked concrete. And I will also talk about the tailored experiment that we use for the validation of this model. So in the presentations of Branko and Erik, you could already see what we mean when we refer to lattice modeling. But to demystify, it's simply we use 3D assembly of monodimensional finite elements, or how we call them lattice beams, to discretize a continuum that in our case it's precisely a cement-based virtual sample. Adding a little bit to what has been already said by Branko and Erik regarding lattice model discretization, as they mentioned, typically a lattice mesh is the result of a Delaunay triangulation based on the 2D or 3D coordinates of nodes placed semi-randomly within a quadrangular cell inside a quadrangular grid. In the case of fracture modeling, our discrete elements are always, or at least so far in literature, we have seen that they are always the Delaunay triangle edges. And the two nodes belonging to the elements possess certain degrees of freedom, such as the displacements in the local XYZ direction and the rotations around this axis. You can see the Delaunay elements in the upper image in the slide with continuous black lines. Now, in the case of mass transport, Branko has already mentioned how the same network of beams from the Delaunay triangulation can be used to simulate mass transport, as if it were a system of pipes that are connected through the nodes. in which the degrees of freedom can be either the concentration of a specific species that we are simulating the transport of, such as chlorides, as Branko mentioned already, or it can be moisture content, or, as you will see later, the pressure of an unwetting fluid, such as CO2. More recently, the dual mathematical operation of a Delaunay triangulation, which Branko already mentioned, and which is called Voronoi tessellation, has been also used for the modeling of mass transport. In this case, the elements are the facets of the Voronoi polyhedra that you can see in dashed lines in the same image before. So it is interesting to discuss these two meshing strategies and see which is the influence of these meshing strategies on the final results. So before we go to actually how to model moisture transport in this context of lattice modeling, I wanted to start by comparing the behavior of these two mesh types even before we called in the governing equation. So you can see when we discretize the same 3D domain, you see presented on the left is the Delaunay discretization of a domain, and then on the right you have the Voronoi tessellation, and we draw a comparison already of how many nodes do you need to include in your model for one and the other, and also the number of elements that these nodes entail. And you can already see that the Voronoi tessellation already has many more, almost sixfold, the number of nodes that you have for Delaunay triangulation with the same starting sets of nodes and for the same domain, which is actually quite important because the number of degrees of freedom of the global system will actually determine how fast or how computationally efficient is your model. And this is especially important when you have or are modeling phenomena that actually are very long term. So you have to run the simulations for a while. So keep that in mind already. So now that we have in mind which way to discretize our continuum, we need to speak about the mathematical formulation of the problem that we want to model. Now, in this case, we are talking about moisture transport and specifically about capillary absorption of water in a cement-based material, which is a porous medium. And we can either choose to have the solution as a moisture content, a volumetric moisture content of a saturation. So I wanted to make this small parenthesis that I will be talking about saturation with values from 0 to 1, sorry. Now, if we are rigorous, let's say, in order to simulate unsaturated moisture transport in a porous media, we are talking about the two-phase flow in which we have one species, which is the moisture, and that we treat through the moisture content or the saturation, and we have the pressure of the non-wetting fluid, which would be air. This entails that we have two partial differential equations, which are tightly coupled, and which is, as Branko mentioned or hinted before, quite more complex than just having one PDE. So mathematicians before us actually solved that problem for us, and through a number of assumptions, and provided that the temperature is kept at 20 Celsius degrees, we can arrive to the so-called Richards equation, which is actually widely used for the modeling of moisture transport in porous media. With this equation, you arrive to a sort of diffusive kind of process of moisture inside the porous medium. And it's quite simpler, as I hinted before. So as let's say, assuming that the temperature is always 20 Celsius degrees, then we are fine and we can solve the problem much more easily than if we had a coupled system of two partial differential equations. Basically, this equation describes the rate of change of the quantity theta, which is the saturation, per unit of time as a result of a diffusion-like mechanism of the moisture due to the non-uniform spatial distribution of theta itself. And of course, due to the presence of sources or sinks, which are included in the equation by the term S, which could represent either chemical reactions where water is being produced or consumed, or other, let's say, physical processes. For example, if we include superabsorbent polymers will absorb water, so therefore they will become a sink. Water is being consumed. But we will see more about it later on. Of course, if we are talking about finding a unique solution of this equation, we need a set of boundary and initial conditions for this. So I repeat, we are talking about capillary absorption of water. Typically for such experiment, maybe you have seen it before. And you have the bottom of the sample, which is exposed to water, whereas all the other surfaces of the sample are sealed. So there is no moisture exchange between the environment that has a certain relative humidity and the cement-based material. So this entails another, the two following boundary conditions. We have first theta, the saturation of all the nodes at the bottom of the sample, that will be 1. And the flux, the perpendicular flux of moisture in all the other surfaces is equal to 0. And this specific boundary condition is automatically satisfied for finite element formulation, so we don't have to take care of it. And then we have the initial condition, which usually for this type of experiments, we precondition the sample in order to have uniform moisture distribution inside the sample at the beginning of the experiment. But as well, you could have, let's say, a space distribution of moisture, let's say, which would be the output of another simulation, and then you can also input these initial conditions like this, and that's no biggie. So the other term that I haven't talked about yet in this equation, sorry, is the function d in theta. D that we will call from now on hydraulic diffusivity is a function of theta, but there is also another part missing here. It's also a function of the transport properties of the material. So how to formulate the hydraulic diffusivity? There are many ways, and the one that I will explain now, it's an empirical law that we will call exponential law of hydraulic diffusivity, that basically describes the variation of D for different moisture, saturation, sorry. And here, in order to take into account which are the transport properties of the material, we have the parameters D0 and N. D0, it's quite comfortable or easily, let's say, identified or measure it by doing a simple capillary absorption experiment and finding the sorptivity, which is actually a quite trivial experiment. Whereas N is typically taken as 6 with actually pretty decent results. So once we have the governing equation, then we can discretize this equation in time and space. I won't go into detail because this is classic finite element formulation derivation, so you can actually consult the book that Branko suggested before, or any other finite element book. You will find even how to discretize a typical diffusion equation that's no problem. And just to mention that we use Crank-Nicolson time-stepping procedure for the simulations from this point on. So now we can go back, or if you will, we can go back to the comparison between Delaunay and Voronoi discretizations of the domain to see how it actually performs when we actually do simulations of moisture transport. So basically, a very simple example. You have a cubic domain where the function of hydraulic diffusivity is equal to the unit, and then we impose a moisture content equal 1 on one side and equal 0 on the other side, and we are busy simulating the steady state of this problem. That means that the time derivative of the equation is 0. There is no variation of the solution in time, just in space. So these conditions allow us to find an analytic solution, which we can compare to the results of the numerical procedure, and then we can find the error norms. So you can see that in the table, I reported the 2 errors for the 2 different discretizations, and you can see how easily Delaunay triangulation outperforms the Voronoi tessellation in terms of quality of the solution, which is something nice, because we saw as well that Delaunay triangulation yields as well a smaller number of degrees of freedom. So we are simulating the capillary absorption of water in mortar, and then Branko already mentioned how it's important that we actually choose the element size accordingly to the problem that we are analyzing, because this will actually have consequences on the quality of the solution. Here I just reported 3 element sizes from 0.25 to 1 millimeter, and you can see that after this is after 60 minutes of moisture transfer, you can see that actually there are almost no differences between the 3 meshes. And this I choose on purpose these small sizes because if you remember correctly, when Branko talked about the explicit implementation of heterogeneities in the model, you want to make sure that the heterogeneity that you are implementing has enough elements to be, let's say, representative of the volume of this heterogeneity in your virtual sample. And therefore, this will limit your choice of element size. We have talked about the most important part of modeling, let's say, mass transports, but actually it is important as well that we talk about the 2 other most important parts. First, we need to input the initial parameters correctly. We can use experiments in order to find these parameters, or let's say reliable empirical relationships. And then the third most important one is that you have a reliable and precise experiment for the validation of your results. Precisely about this last part regarding the validation of the model, we designed an experiment that actually helped us to do so. These experiments involved X-ray computed tomography to monitor the distribution of moisture during capillary absorption of both sound and cracked samples, mortar samples. This experiment was done in collaboration with the geology and physics departments at Ghent University. And now I will devote a little bit of attention to the methodology that we use for carrying out these experiments. before comparing the experimental and the modeling results. So a little break from modeling, here it goes. So we are busy with the problem of imaging water in the porous mortar matrix. So let's reflect a little bit on what we need for such an experiment. So typically, concrete has multi-scale porosity. Pores in concrete range from nanometer size in the gel to micrometer scale capillary porosity to macropores that can go to like the scale of centimeters. So what do we ideally need for imaging moisture transport in cement-based materials with such a multi-scale porosity? So first, we need contrast to small changes in 3D, why not, of pure water content. Second, we need at least a couple of nanometers of spatial resolution. Then we need minute scale time resolution. So we need to be able to complete one scan, 360 degrees of the sample within 1 minute. And then, of course, we need to repeat the measurements on a large enough statistically relevant number of specimens. So what we have available in let's say the state of the art regarding imaging of such a problem, we can list neutron tomography. This is quite nice because you can see quite a contrast between water and solid matrix. But alas, it is very difficult to access. You have to ask for beam time. You have to really have a sharp, bulletproof methodology, because if you fail, you have to ask for beam time again. And this is not quite easy. And then the other problem is that you typically don't get a high space and time resolution, which is not nice for our problem. Then you have MRI, magnetic resonance imaging, which is even more difficult to access. Typically, this kind of equipment is mainly in medical facilities and is also very, very expensive. And then we have X-ray tomography, which normally doesn't have high enough space and time resolutions. And it also presents poor contrast between cement and water. But X-ray tomography, it's the most accessible and cheapest at lab scale, with almost every, let's say, university. I don't want to say every university, but let's say there is more access to X-ray tomography in a university than any other equipment that I mentioned before. So what can we do in order to use X-ray tomography to actually monitor 3D moisture transport? So we can settle for above pore resolution, so we won't be able to see water inside a pore, let alone the pore itself. But we can optimize the time resolution for a good enough image quality. And we can use the attenuation differences between wet and dry states of the material in order to see the differences on moisture content. So for this experiment, we prepare mortars with different water to cement ratios. These were the samples. They were cylindrical with some grooves on it. These grooves were designed on purpose because we wanted to scan both uncracked and cracked samples. And these grooves allow us to create a nominal crack width that was quite within a certain target standard deviation, which is actually, if you know what I'm talking about, quite difficult to obtain in our field. So this was kind of necessary. So we preconditioned the samples. So as I mentioned before, it is easier to have a uniform moisture distribution inside the sample for a capillary absorption experiment. So we dry the sample at 40 degrees, least harsh as possible. And then when we obtain a constant mass, we seal the sample and then we leave it in the oven. So this moisture can actually redistribute uniformly. In the case of samples that we wanted to crack, we perform tensile splitting test, and then we obtain, let's say, the 2/2 of the sample, and we calibrate the crack, glue around this metallic strips in order to keep the crack, and take out these metallic strips, and then we seal all the lateral surfaces. So typically, if you do X-ray microcompute tomography, the first step is the acquisition. So imagine that you go to the doctor because you have a broken bone. If you have had that experience, you will remember they hand you a 2D, let's say, picture of your bone. And in this case, what we do is that we do 2D images at different, let's say, angle steps during the rotation of the sample. This way you have a group of projections, of 2D projections, that then you can let's say, put together and reconstruct a 3D volume. And this is what we typically call 3D reconstruction. And almost all lab scale X-ray micro-CT have their own reconstruction software, and specifically the one I used for this experiment had already implemented inside beam hardening corrections, ring artifact correction, and spot corrections, which are typical artifacts that have nothing to do with the physical process that we are actually analyzing, and therefore need to be left out. And then the special step that we had to do here, because as I mentioned before, we are scanning the same sample at different stages during water absorption. Therefore, we need to make sure that each scan is positioned, let's say, in such a way that the same domain of the material, the same small part of the material, is represented in the same position in each of the scans. This is very important, especially if you want to quantify the differences between one scan and the other. So this is the CT scanner that we used. This is in Ghent, and this scanner is quite special because instead of the sample rotating in the middle, which is the typical configuration of a lab scanner, this specific scanner has a gain tree that aligns together the detector and the X-ray source, and this is the one that rotates around the sample. This is quite nice because when you are scanning dynamic processes, you need to make sure that you are not scanning, let's say, phenomena that have nothing to do with the experiment that you are studying. So in this case, for example, you can see the scheme of the cell that we put in the CT scanner. And if we rotate the sample, we can have some inertial movements of the water, which is not what we want. So then, what did we do? How does it work, this experiment? We scan the sample at the beginning with a certain known very low moisture content distribution, and then we scan very fast with each scan within 18 seconds, continuously for the first 10 minutes, because that's quite fast what's happening there. And then after 20, 30, 40, 50, and 60 minutes of water absorption. So we have these couples of CT scans, and what do we do? So we exploit the principle that, let's say, the attenuation coefficient of a certain pixel at a certain time can be formulated as a linear combination of the attenuation coefficients of the different phases in that pixel, which in our case will be cement, air, and water, and their volumetric ratios. And this holds for every step of the way. But especially for the beginning, when we know how much of each phase we have, at least in average, and then we can subtract this quantity to any given time, and then we can isolate the volumetric water content at a certain time, and we obtain this formulation. Because we can draw the parallel that the attenuation coefficient translates linearly to the gray value that we obtain on that 3D reconstruction. So we can summarize any given scan, a CT scan, with a histogram, which is a distribution of the gray values in the scan. And you can see in the left graph the histograms of one reference scans, so the dry one, and the target one, which is at a certain time. I don't remember which one I reported here. And then you can subtract these two and obtain the moisture content distribution, which you can later transform to saturation by dividing by the porosity. So now the results. So these are results for the samples that are not cracked. So on the left graph, you can see that we also compare the CT measurements with a gravimetric experiment, which is just basically measuring the mass that the sample acquires along the capillary water absorption. And then you can see that whereas after 10 minutes or so of water absorption, the results are quite close to both gravimetry and CT, whereas at the beginning you have this discrepancy between CT and gravimetry measurements, which is actually due to the fact that at the beginning you don't have much moisture transport occurring, therefore the noise to signal ratio is quite high. But let's say that it was successful. Still represents what's happening in the material afterwards. And then on the right graph, we put together the vertical profiles of moisture content of both the CT and the simulations. And you can see that again, there is a discrepancy at the beginning, but that was no surprise because we could see it from the graph on the left. But then later you have a good correspondence of both profile types. Well, this was an animation to see in 3D how the water penetrated the material, and you could see the differences between samples with different water sample ratios, but this is a PDF, so you cannot see it. I wanted to expand a little bit on what Branko was commenting about implementing heterogeneities in the material in order to see how these heterogeneities influence the transport mechanisms. I wanted to report an example of some simulations of a cement-based material with large aggregates and how these large aggregates impact the transport. And we compared two experiments that were available in literature, and you can see that there is a good correspondence, so the model can actually capture quite well what's happening when you include aggregates. So you can see here the cumulative water absorption for different volume fractions of aggregates, and you can see that the higher the volume fraction of aggregates, the slower the cumulative water penetration is. This actually helps us to understand which are the mechanisms for which this happens, and this is not possible to, let's say, to draw from an experiment. You can draw conclusions, but which specific mechanisms are acting, this is actually quite nice to do by modeling, because you can play with a lot of parameters and let's say save a lot of time and effort. So we can see for the way that we implemented the model. So we implemented IT set around the aggregates, and therefore there applied the higher hydraulic diffusivity, and then also saw how this influences the cumulative water absorption. And you can see that if the IT set hydraulic diffusivity increases, of course this will increase as well the pace of this cumulative water penetration, but not as much as when you actually decrease the number of aggregates. So you can see which is the influence or the weight of each factor on these transport mechanisms. So we talked about how it was actually more convenient to use Delaunay discretization rather than Voronoi for uncracked material. But what happens when we have a crack? So imagine that you want to have a coupled, you want to model a coupled phenomena. Let's say that you do a fracture simulation with a lattice model using the Delaunay elements, and then you want to simulate moisture transport because you want to see self-healing later or for whatever reason. And then you can see in the lattice, the elements that are marked with a discontinuity, these are the elements that as an output of the model are cracked. But when you want to simulate transport with these same elements, you can see that actually, because they are like connected pipes through which the moisture flows, let's say, the physical path of the crack is not really respected. So there has been much discussion in literature whether to use this dual Voronoi discretization in order to overcome this limitation of the other discretization. So we use two approaches to model water transport in the cracks. So the first approach we do like this. We say, okay, this crack is a porous space in the mortar, and it has the hydraulic diffusivity that depends on both the moisture content in the crack at the moment and the crack width. This has been used before with decent results. And then the second approach that we came up with was to use the modified Lucas-Washburn equation, which was proposed in a paper from Gardner and co-authors in 2012. So basically we model which is the capillary rise in the crack, so just the height of the water column in the crack, and then we apply a boundary condition in the crack accordingly to this water rise. So now we can compare experiments and model for the cracked example, and then you can see that actually there is quite a nice correspondence respect to the water penetration perpendicular to the crack. But again, at the beginning, this is lacking correspondence. We already discussed about it in the sound sample, and it is difficult actually to eliminate the noise when you have such a large noise to signal ratio. If we use approach number 2, there is not much that changes because actually what you obtain from that model is the height of the capillary rise versus the time. And you can see that for this specific case, for this specific crack width, which was, if I remember correctly, 300 micrometers, the capillary rise is 50 millimeters, whereas the sample height is 10 millimeters. So the crack will fill quite fast, already in 2 seconds, with the water column. Therefore, there is no point on comparing. But this approach is especially, let's say, useful for when you have a tall crack. So you have a larger sample, not a tiny one. And then, so on the right, you see the graph, the input of this first part of the simulation, which is the capillary rise. And here, the variation is a little bit slower because the crack is also higher. And then you can see the differences between the approach 1 and the approach 2. So you can see in the approach 1, this goes quite slow, which is not representative of what really happens in the crack. And in the approach 2, you have that immediately the crack is filled to a certain point, and then it keeps going. And you can see that there are differences even on the long term after 60 minutes of water penetration. Sorry. So you have more water penetration where, of course, you have the crack filled right away, which is what physically happens in this case. Okay, so this is the first part of my presentation. I don't know if we should do a break now or it is not necessary. What do you think?
How much time do you still have?
Yeah, maybe 20 minutes or 30 tops.
Can I do my part?
No, I can continue, no problem. Just wondering if someone wanted to go to have a break or something. Okay, I will continue if no.
Yeah.
If no one comes forward. And Branko, then maybe after this part you can do, you can talk about the modeling of self-healing with capsules.
Okay.
Yeah. Okay, so in this second part, I will be presenting some results of a study we performed to model the crack self-sealing in mortar with superabsorbent polymers. So I don't know how familiar are you with superabsorbent polymers, but they have been quite popular for concrete. They have been used for mitigating early cracking due to their internal curing functionality. But also recently they have been used for crack self-sealing and later on crack self-healing as well. Basically, these polymers absorb water because of osmosis. You can actually read a little bit more into it if you are interested. And then while they absorb water, they also swell. And this, you can imagine how could be attractive in terms of self-sealing, because imagine that you add the superabsorbent polymers in a mortar when you are preparing it. These superabsorbent polymers will absorb water during mixing of the cement and the aggregates, etc. And when the sample is cured and dry, these superabsorbent polymers will release the water and they will shrink, leaving a macropore behind. When cracking occurs, let's say, these macropores actually constitute weaknesses in the material, which can actually steer the crack patterns along this network of macropores. And therefore, a lot of these superabsorbent polymers will actually be exposed in the crack, which is quite handy because when water penetrates in the crack, you have the superabsorbent polymers absorbing the water and at the same time swelling. And ideally, we would have this superabsorbent polymer gel expanding within the cracks and blocking the flow of water coming in. So how to look at this through lattice model eyes, let's say. So we have we can model the fracture of a virtual element with a lot of superabsorbent polymers, and then we can simulate capillary absorption and see and simulate as well how these superabsorbent polymers expand in the crack and how these at the same time can modify the moisture transport phenomena occurring both in the crack and in the matrix. So we again use the Richards equation for the moisture transport, And in this case, we will be making use of the sink term, as I already hinted before. And then, of course, we here treat the crack domain as a porous phase, and we model as well the moisture transport within the cracks. That was quite important for this specific phenomenon. And then we need a function with which to evaluate how this sink term work. So we used the results from a study by Esteves in 2011. He proposed an experiment in which he monitors the swelling of superabsorbent polymers in a pool of water through microscopy, and then he arrives to the curves of the type shown in the graph on the right, which can be later, let's say, used to find out the rate of absorption of water of the superabsorbent polymers. And then that's what we use actually for the absorption of water and the swelling of the superabsorbent polymers. So how to implement this numerically? We modeled the superabsorbent polymer particles with the A&M model, and basically we use this model because it is nice to recreate the superabsorbent polymer regular shape. This later on performs a non-overlapping parking procedure, therefore there are no two particles actually compenetrating each other. And then we use the discretized model and the linearized Krag-Nicolson procedure to model the moisture absorption in the matrix. But we also have the sink term that we need to discretize. Now, before we continue, I didn't have a nice scheme showing this, but the way that we implemented this, the swelling of the superabsorbent polymers and how does this influence the moisture penetration in the crack and therefore later in the matrix, is what we do is that we simulate the moisture uptake by these superabsorbent polymers at the same time that in the matrix, and then when they absorb water, their volume also changes. Therefore, we engage elements that before were cracked elements by reducing the crack width of the amount of superabsorbent polymer volume that has increased. So more or less, this is how it goes. And then, of course, the transport properties of these elements change from having a certain hydraulic diffusivity, which is high because it's a cracked element, to a lower hydraulic diffusivity because this element is no longer cracked. It has a superabsorbent polymer gel in it. So first, we model the capillary absorption of water in the uncracked sample with superabsorbent polymers in order to see if actually this law of this rate of absorption of the superabsorbent polymers worked okay. And we use input data from a study from Snook in 2015. He had mortar samples with superabsorbent polymers, 1% by way of cement. And he also had two reference mortars, from which one had the same effective water-cement ratio as the one with superabsorbent polymers, and the other one had the same total water-cement ratio of the one with superabsorbent polymers. So you can see that the model actually is quite close to what he measures through capillary absorption experiment. You can see that the model could capture well this steeper initial portion of the curve, which can actually be attributed to the fact that superabsorbent polymers that are near to the boundary that is exposed to water absorb water and swell quite fast with respect to the absorption of water by the surrounding matrix. And then the change of slope on the curve is also captured in the model, which actually confirmed that the law that we use for modeling the absorption of water in the superabsorbent polymer was okay. So now, in order to model the absorption of water in the crack by the superabsorbent polymers, we need extra data. And because we have seen from experiments in literature that even though what we want is to have all these superabsorbent polymers swelling and going all around the crack, this is not always the case for all the superabsorbent polymers. So you can see in a study by Lee and co-authors that they have a lot of swelling. You can see the first image on the left. Whereas this other experiment by Hong and Choi in 2016, you can see that, okay, there was swelling, but the swelling was ascribed to the macropore that was cracked in the middle. So a lot less. So we had to measure this, which is the absorption capacity of the superabsorbent polymers in the crack, because they are also constrained by the crack walls, and there are a lot of forces in play here, not only osmosis, but you also have mechanical forces that counteract this swelling of the superabsorbent polymers. So what we did, we kind of drew inspiration from Hong and Choi, and then we did a CT scan of a saturated sample with superabsorbent polymers, the ones that we were studying, specifically the ones that Snook used, and we showed the results as well for the sound samples. And we used statistics to determine which was the ratio between the absorption capacity of the superabsorbent polymers in the crack versus, so the ratio between this and the absorption capacity of the superabsorbent polymers during mixing of the concrete, because as you can imagine, you have to take into account that there is a macropore that is traversed by the crack. And this, yeah, originally we would not consider crack, but it actually is. Another thing that we need in order to model the self-sealing process and its influence on the moisture penetration perpendicular to the crack, which is actually, let's say, the functionality that we want to improve with self-sealing. We also need the transport properties of the matrix, and this we obtain from the same actually validating experiment that we used, but instead of from the transport perpendicular to the crack, from the vertical moisture penetration. So what we did, because we didn't have the transport properties of this specific matrix, we fit the experiment for this portion of the sample with the model, and then we can back calculate the hydraulic diffusivity. And this is an example of how you don't only use modeling to simulate a certain experiment, but also you can use it to find properties that otherwise will be difficult to measure, or in some cases even not possible. So finally, this is the comparison between the experiments and the simulations of self-sealing. So maybe you're not familiar with the experiment. So basically, Snook, what he did was to monitor in 2D the water penetration on a crack sample with superabsorbent polymers. So we can compare the simulation results and the experimental results, and they're actually quite close, which is nice. So the nice thing about modeling, as I mentioned before, is that you can find the influence of each parameter in the final result, or at least speculate about it. Things that you could not isolate in an experiment, you can actually separate the influence of the different factors while modeling. So what I report here is a comparison of different types of samples. So B1.0 is the sample with superabsorbent polymers, both in the crack and in the matrix. Ref S is a sample that contains superabsorbent polymers only in the matrix, but not in the crack. And the ref is then a sample that has no superabsorbent polymers whatsoever. And then we can see what's the influence of the presence of superabsorbent polymers both in the matrix and in the crack in this perpendicular penetration of water to the crack. And you can see that at the beginning they are quite similar. These are different time steps. But then as time goes by during the simulations, you can see that the self-sealing does influence the horizontal penetration of water during capillary absorption. And the presence of superabsorbent polymers in the matrix as well plays a role in it, in delaying this moisture penetration. So now that we have validated the model, what we can do is to analyze other parameters that could be used for designing an optimized self-sealing system. So, for example, if we look at the ratio between the absorption capacity of the superabsorbent polymers in the crack and the absorption capacity of the superabsorbent polymers during mixing, you can see that it's actually a parameter that can be used for the design of such particles, or at least for the choice of the particles that you can use for such a system. And before we used 1.37 because that was what experimentally we determined, but then we increase this ratio and we can see which are the results. These are the moisture penetrations after 60 minutes of water absorption. And you can see, of course, the benefits of increasing this ratio. I report as well the, let's say, volume of superabsorbent or of swollen superabsorbent polymer in the crack for each of the cases. And you can see, of course, why is it that we are blocking the water penetration for each case. So another parameter that is actually easy to change is the dosage that we use of superabsorbent polymers, because ideally, we want to have enough that are perform well in terms of self-sealing, but we also don't want to add so many because this will affect the mechanical properties of the system. And of course, this comes with an additional cost as well. So you can see that before we had 1%, and then I report as well 0.5% by way of cement and 1.5%. And you can clearly see the differences, and you can quantify how much the transport in the matrix changes by just adding or taking out superabsorbent polymers. The last parameter that we analyzed was the crack width. Before we had a crack width of 200 micrometers, and you can see that maintaining, of course, the same ratio of absorption in the crack versus absorption in the matrix, and the same, of course, dosage of superabsorbent polymers. While we increased the crack width, of course, we obtained a decreased functionality of the self-sealing system. But it's also good to have in mind this when you are designing such a system. And we can draw such optimization surfaces that for each of the crack widths that can actually help us choose, okay, which is the trade-off that we are willing to do to obtain a certain functionality. Branko, you can step in now.
Yeah, thanks, Claudia. I just have a few slides.
Yeah.
But maybe I hear it myself in the microphone. Let me try to share. I hope you can see my screen.
Yes.
Just very shortly on how you can also use modeling to design self-healing materials. So Claudia already showed one example where you start from a material that you can buy or synthesize in the lab, this SAP, and then you can optimize based on the how much you need it, on the particle size distribution, on the swelling capacity. Then you can go back to the lab and adjust the chemistry in order to achieve that swelling capacity that you need. But there is other mechanisms that we could use, and maybe you can use modeling to optimize those. So just shortly to show a bit about that. So typically, when we think about self-healing, we think about two different approaches. One is a capsule-based approach where the capsules are spherical, or another approach is with tubular capsules where the capsules are more elongated. And depending on which self-healing mechanism you prefer, one or the other is better for you. But there's also geometrical effects that are there because you also need your self-healing mechanism to activate actually when you have a crack. And typically, very simply, we use this type of model to see how much of our cracks, how much of our self-healing agent will be activated. And then we assume that there is a planar crack and then that it sort of cuts through all the self-healing capsules that are in that plane. But this is not really the case. As you saw already yesterday during the experimental part and today during Erik's presentation, cracking in concrete depends on the microstructure and the interaction between different parts of the microstructure. So actually you need to make sure that your crack penetrates through your capsule in order to activate your self-healing agent. In case of SAPs, it's also okay that it goes just next to it because you just need the surface of your SAP to be exposed to water. But if you have a capsule that has, for example, an adhesive, you need the capsule to break in order to activate the self-healing agent. So we wanted to see what can we do in terms of modeling to enable this design of such materials in the lab. So other thing that your capsules need to be able to, they need to survive the mixing process of the concrete. So even if your capsule is very brittle, you are sure that it will break under cracking of concrete. It might break also during mixing and placing of concrete. You also need to make sure that the capsule material, the shell material, does not react with the healing agent and or the cementitious matrix, because you don't want your capsule to dissolve by itself, for example. Furthermore, you need to protect your self-healing agent from leaching and oxidizing, because it's known that some adhesives, actually most adhesives, have a relatively short shelf life because of oxidation. You don't want that. You want your material to be active for a number of years, because you might need to heal cracks that occur at a later stage of the service life. And what you also want it to break when a crack occurs, which is typically what we first think of, but it's also related to the other. So you need a very specific material. Some materials that use for capsule making will survive the process of mixing, but will not break when the capsules break, when the concrete breaks. So that's not what you need to find the balance between these two. So what can happen when a crack occurs in a material? There's three cases if you simplify it. One case is when a crack penetrates through a capsule. In this case, your healing agent is released. Another case is when a crack goes around the capsule. So in this case, you can have a lot of cracks, but a lot of self-healing agent, but all the cracks go around them, nothing will happen. And the third case is when you have debonding of the capsule. In that case, some self-healing mechanisms are okay, for example, SAP, while some still are not activated by this, for example, encapsulated adhesives. So you need to make sure that you design a material that you can have a self-healing mechanism activated. Now, in this study that I will shortly present to you, we were looking into different materials that were used to create tubular capsules, so elongated capsules, and then filled with adhesives, but we were focusing on the capsule material. So these capsules were extruded. That's why they're sort of elongated. They have different capsule walls, and they're made of different polymers, different materials with different properties, different tensile strength, elongation and break, and Young's modulus. So we put these into our model and try to see which capsules can actually break. So what we did first, we measured in dog bone specimens the stress and strain curves of each of these materials, so we know the material properties. So for example, for PLA, PMMA, and so on. And then we implemented these in a very simple lattice mesh. So we implement one long capsule in a block of mortar, and then we subject it to uniaxial tension. And we measure the crack width here. And we see at which crack width will the capsule break, taking into account the geometry of the capsule, so the thickness of the wall, its diameter, but also its mechanical properties, so the stress and strain curve. And this allows us to sort of save a lot on the experimentation, because we can already discard those that will not work, and then only focus on those that might. And actually, we saw that as we expected, glass will break at a very small crack width, which is great for self-healing activation, but glass will not survive mixing of the concrete. So on the other hand, PMMA will break at very large crack widths, so that's not good, because you want your material to break at small cracks. So it will survive the mixing process, but it will not survive. It will not be useful actually for your self-healing. So you want you can use this type of diagrams to actually design your materials, and we then compare that to a set of experiments, and we all actually saw that our model, very simple, showed quite good correlation with the experiments, and that sort of gives us confidence that we can use these types of simple approaches to design capsules for self-healing concrete. And you can do the same. We have not done it, but you can do the same for spherical capsules. You can play with the parameters, elastic moduli, content, and also the strength of the capsules, and see how that affects your response, and how many of your capsules will actually break under different conditions. So in short, modeling and this type of relatively simple modeling allows you to optimize the capsule design, the geometry, and the materials that you use for capsules, to optimize the self-healing agents that Claudia will show you in a bit, the amounts of capsules. So if you have spherical capsules or SAPs, as Claudia showed, you can end up with sort of a design surface that will tell you how much capsules you need for a certain self-healing efficiency. And finally, and most importantly, I think, because in any case, you need to do experiments. This will allow you to save time and costs on experiments, because experiments cost time, but that also has a financial cost as well. So this was a short interruption of Claudia's talk. I hope it is clear. And if there are any questions, please feel free to post them in the chat. I am done, Claudia.
Yes, I'm trying to put the. Oh.
I'm trying to open the chat. If you have questions also at a later stage, feel free to email me. There is okay, maybe I'm in a wrong chat. A virtual break. Okay. Okay.
All right. Thanks, Branko.
I have to leave now. Sorry.
Okay.
Let me know if there are
okay. Thanks, Branko, for today. Thanks. You have to pick up Luca.
Yeah, I have to go before they close the kindergarten. Bye.
Okay, bye.
All right. Okay, so I will go briefly through something I've been working on, which is the implementation of lattice modeling for the simulation of carbonation in cement-based materials, and therefore to create a baseline for the modeling of autogenous self-healing. And I will talk a little bit more about the methodology because actually I was supposed to talk about self-healing, and this is a little bit farther. But basically, why is this the modeling of carbonation relevant for the modeling of self-healing, where calcium carbonate is the healing agent? It's because actually the most successful, or one of the couple of the most successful autonomous healing mechanisms that have been proposed in the literature so far actually involve the carbonation of the crack. And examples of such self-healing mechanisms can be the addition of crystalline admixture, which basically you add a further amount of the calcium ion source. We can mention as well the addition of bacteria to promote crack carbonation, and the joint action of PVA fibers and superabsorbent polymers. So in order to model carbonation, you need this time a little bit more complex system. So you have to call in the mass balance of the different species that participate in the reactions. So that is the moisture content, again, the saturation, the partial pressure of the CO2 gaseous, and the concentration of calcium ions in the pore solution. So let's talk a little bit about the mass balance of water. What changes here with respect to what we were discussing before is that we have a source term. This source term is because when calcium and carbonate ions react to form calcium carbonate, water is produced, and this water adds into to the moisture that is present in the domain at that time, and then we need to include as well that. Then we have the mass balance equation of the carbonate in gaseous state, and in this case physically we have two types of fluxes. So we have a diffusive flux and an advective flux, but for this specific case we assume that the advective flux it does not contribute as much to the carbonation process, because the dissolution of CO2 is actually quite slow, and therefore the reaction occurs quite instantaneously when this dissolution happens, and therefore it doesn't get to be transported by the flow of moisture in the material. But the diffusive flux is actually quite important, because this will determine the presence of the CO2 in your unsaturated medium, and this will depend as well on the porosity of the material and on the moisture content. And then we need to consider that because CO2 is participating in the reaction, there will be a sink term that actually tells, hey, here we are consuming CO2, in this case carbonate ions, in the reaction in order to give to precipitate calcium carbonate. And then at last we have the mass balance of the calcium in the pore solution. And in this case, we can no longer neglect the advective flux of calcium with the speed of the moisture flow, because this is quite relevant here. The calcium dissolution from the hydrates, it's quite faster, so there is a lot of time for it to actually transport through advection to other parts of the domain before the reaction occurs. So this needs to be considered, and it's the second term in the brackets. There is as well diffusion, so this is driven by the presence of a gradient of calcium ions. during the mechanism. And then this diffusive flux will be influenced again by the porosity and as well by the moisture content. And in this equation as well, we have a sink and a source term. The sink, again, we make reference to the reaction going on. So calcium carbonate is being created from the reaction between calcium in aqueous solution and the carbonate ions, and therefore we need to represent this with a sink term. And then we have a source term because this calcium in the pore solution is being replenished by the dissolution of cement hydrates, which at the same time depends on the calcium concentration in the pore solution. So now that we have the three equations of this system, we can draw a parallel to what we have been discussing this afternoon. So we can, before, for the fracture, we had certain degrees of freedom, so the displacements and the rotations. If we model the, say, capillary absorption, we need only the saturation of the nodes that we called before as theta. But for this, we need, for modeling the physical-chemical healing process in the future, we need these three species. They are the solutions we are looking for. So we discretize in space and in time this equation, this governing equation, again using Crank-Nicolson, and this is where things get more complicated because here we have a nonlinear system with a semi-implicit time-stepping procedure, which actually obliges us to use iterative solver. Typically, such nonlinear systems are usually solved through Newton method. So basically what Newton method says is that we can approximate the residual. By residual is, I'm referring to the first equation, is basically the governing equation that is equal to 0. And then the Newton method, what it does, it does approximate this residual to a Taylor expansion truncated after the first derivative of this residual evaluated on the previous solution. So once you rearrange the terms, you can, and you call this first derivative evaluated on the previous solution Jacobian matrix, you can solve this system by finding this delta U, which is the solution, which contains the saturation of the nodes, the calcium concentration, and the partial pressure of the CO2. So basically, in an iterative procedure, you try to diminish this R0, which is the difference between this left-hand side and right-hand side. But this is not quite trivial because sometimes, depending on the system that you have, deriving the Jacobian matrix is really difficult and quite consuming if you do it numerically as well. So we choose to use Krylov subspace iterative solver called generalized minimal residual method, in which you don't have to find this Jacobian matrix. Instead, you only find the matrix vector product. So the J, it's as a subspace of linear combination of this product. Then when you find, let's say, a delta U that actually satisfies a certain tolerance that you put low enough in order to maintain the quality of the solution, you can continue to perform the different Newton steps and so on. This is still very complicated, and you need to do a lot of mathematical tweaking or numerical tweaking in order to have sound results. So first, you may encounter that the starting solution, which is the initial solution, is far from the solution that you want at a certain Newton step, and this needs to be solved. Sometimes you have that the source or the sink terms actually grows much faster than other terms, and this will give you trouble because then you have different terms in your system of equations that are magnitude-wise very different. So you can implement a series of different tweaks, like for example using globalization of the Newton method, that is decreasing the size of the step that you find with each Newton iteration. You can under-relax the source or the sink terms, which actually it's equivalent to have 2 time scales, one for the source terms that are actually some of them quite fast, and one for the other terms of the equation. And you have to precondition your system as well. So this is the flowchart. If any of you is interested, you can check it up in the slides. So we wanted to validate the method with and what we need as input is, of course, the porosity. In some cases, in this case, we include the tortuosity, the permeability, the water retention curve, which basically tells you how the capillary pressure varies with the moisture content, the relative permeability function, and the initial cement hydrates assemblage. And of course, you need to have a well-defined experiment with certain boundary conditions, such as the concentration of CO2 in the environment, the relative humidity, and the temperature of the experiment. So we used the experiment done by Adenot in 1992. And here he had all the input parameters, which was nice because then we can directly implement this input in the model and then compare the carbonation depths at different times for this specific material. And the other thing that is quite important is how to describe these source and sink terms. So basically we took inspiration from Adenot himself and a study from Barry and Cellier, in which they envisioned this dissolution of the cement hydrates with a chemical zoning description. So basically they said for a certain calcium concentration in the pore solution, these are the phases. By phases, I mean Portlandite, CSA, JFT, and AFM that actually dissolve, and with which rate do they dissolve. So then we can obtain how much calcium can be, let's say, can be created at each time. And then we compare the carbonation depth for the model and for other modeling results and the experiments, and you can see that actually the correspondence is quite nice, even though if we have only these experimental points. In the future, I'm trying to optimize the numerical procedure better, because already like simulating these 30 days of carbonation took quite a while. So this needs to be optimized because, as I mentioned before, this is a very long-term experiment, which is actually quite relevant, and as well for the implementation of cracks in this model, this will add degrees of freedom and therefore will become even more difficult to simulate these long-term experiments. So I will stop for now because you're probably very tired already. I am tired. And we can discuss a little bit about the questions that you guys have, and as well going back to the discussion points that I was talking about before.
Okay, thank you, Claudia, for this very nice overview of what you are working on. Are there questions now or points to add to the discussion?
So there was a question by Wavi before regarding the self-sealing model, I guess. Wavi, are you there?
You cannot hear her. She's in the live event. So she can only type questions in the Q&A.
Ah, okay. Oh, pity. Well, Wavi asks if I could go to slide 43, because I mentioned that the absorption of the SAPs is constrained by the crack. And she asked, or he, sorry, I'm not sure, he asks what factors constrain the absorption of water by superabsorbent polymers. So I'm not a chemist I'm not an expert as well on this polymer chemistry, but basically the main driving mechanism for superabsorbent polymers to absorb a certain solvent is osmosis. But this is not the only driving mechanism that allows the absorption and swelling of superabsorbent polymers. You have elastic forces in play as well, because these polymers are cross-linked polymers. They are formed by many polymeric chains that are actually cross-linked. That means that they have very strong covalent bonds. The level of cross-linking depends on the superabsorbent polymer that you are studying, but basically they have a certain level of constraint, mechanical constraint by these covalent bonds. So this is what I meant when I said that the crack will constrain the absorption of the superabsorbent polymers, because the equilibrium of these superabsorbent polymers depends on all these factors as well. I hope I satisfied your question.
Well, 3 new ones.
Going. Ah, okay, it was she, no, it's okay, wow. So, well, if there are no other questions, maybe we can, I know you are tired, guys, but I'm still curious whether you are planning to use modeling in your work, even though just briefly you can mention, yeah, I want to model this, even though if you don't have any idea on how to do it, because I know you just started. But it would be nice to know if you actually drew some inspiration from today's lecture or not. Come forward.
I think it's too late, Claudia.
Yeah, or that we could not inspire them.
No, I think that they will use modeling.
Okay, I also
So,
left some question for the assignment. You can go through it. It's not that difficult. But yeah.
okay,
thank you for your attention.
Thank you very much for being here, Claudia, and giving your presentation and sharing your thoughts about modeling. Well, that will also end our meeting for today. It's 1 minute past 6, so it's good time to end. I hope to see you all back tomorrow morning, fresh and lively at 9 o'clock, and then we will talk about making concrete, which is of course very important, because if you don't know how to make concrete, we also have no reason to self-heal it. So making concrete is important. So see you all back tomorrow morning. Bye.
See you.
Bye.
Bye.
Bye-bye.
Bye.
Bye-bye.